everybody to the tutorial session. It is my great pleasure to introduce today's tutorial session speaker, Wei Ji Ma. Dr. Ma has got his PhD in physics, and he has done his postdoctoral training in computational neuroscience with Christopher Koch, and then with Alex Puget. He's well known in this community, really doesn't need much of an introduction. Among other things, he's an expert in Bayesian modeling. He's modeled everything from sensory perception and confidence and behavior and all that. And we are super lucky today to have him for a lengthy 4 hours of tutorial session. We're going to have a great session. And yeah, so please welcome Dr. Wei Ji Ma.
All right. Thank you so much. This might be my biggest tutorial audience ever. It's also the longest tutorial I've ever given. I don't know if you realize what you signed up for, what you actually have to do work. So if you're not seated in one of those weird circles, please go sit in one of those circles. So people in the back rows, please move towards one of the TAs. Could the TA stand up for a moment? So we're very lucky to have 7 TAs for today. And the groups are numbered 1, 2, 3, 4, 5, 6, 7. So it goes like that. And the only reason I mention that is so that you know your TA's name. So it's as in this list. If you haven't yet, can you go to the website and download exercises? And if you want the slides are also going to be up front here, so you don't have to download those. So why do we fit models? Why do we fit models? So this is a quote. You have to start with a quote, right? The purpose of models is not to fit the data, but to sharpen the questions. It sounds very wise. It's said by some famous statistician. There's too much buzz in the room. So what's going on? Like, still no problems connecting, or? Okay, so if it's just slow, don't worry, because in the first half hour or so, we won't be needing the file. So just let it do its thing in the background while you listen to me. If you cannot connect all together, then yeah, just keep trying or ask your neighbor. Yeah, is that okay with everyone? More existential doubts at this point? No? All right, let's continue then. The purpose of models is not to fit the data, but to sharpen the questions. So I see the truth in that. Maybe it's a little bit exaggerated. I think fitting the data is also nice. I'm personally more a fan of this quote. So if a principled model with a few parameters fits a rich behavioral data set, I feel that I really have understood something about the world. And this was said by Wei Ji Ma at Cosyne tutorial 2019. So why do we fit models? A student in my lab did a survey. So these are the anonymous responses. Maslow's hammer, because we're good at it, to drown a conceptually uninteresting question in math, or because Wei Ji says so. That's my favorite. There were also a few more serious responses. So to quantify evidence for our theories and hypotheses, because we want to infer latent variables mechanisms, infer what's really happening in the black box, and then models let us ask questions that are hard to answer with experiments. You can also ask, say, to make predictions for new experiments. So those are all good reasons to fit models. So the models that we're going to talk about today are mostly at the behavioral level, right? So if you came here for a tutorial on neural models, this might be a good moment to leave. No, just kidding. So the behavior for us is going to be the starting point, but of course, eventually we hope that we can also connect these models to the neural basis. So the schedule for today is that we're going to do an introduction. We talk a bit about illusions, just to wake you up. Then we're going to talk about two case studies, Gestalt perception and motion sickness. All these cases are designed to illustrate some central concept in Bayesian modeling. But it's going to be very hands-on and very concrete, because I'm not much of an abstract thinker. In the second hour, we do more cases. Your TAs are going to play an instrumental role in helping you with these cases. In the end, by popular demand, actually I don't know if there's popular demand, I just assume there is, we're going to talk a bit about general model fitting and model comparison techniques, and then in the end you can vent about everything you don't like about Bayesian models. I can do that myself too for a very long time. Okay? So let's dig right in. Why Bayesian modeling? So broadly speaking, you can think of two kinds of models, both in neuroscience and in psychology. So you have descriptive models, which are just attempts to describe the data using some function that usually has parameters. Okay? A very good example is neural networks. Right? They have tons of parameters, and they often do a very good job in describing the data. Now, the danger is, of course, that you would arbitrarily throw lots of parameters at the problem, and that causes issues. It could cause issues with interpretability, which is a big thing for neural networks, and also generalization. So does your model transfer to another task? On the other hand, there are more process models, and those are typically used by psychologists and cognitive scientists, which are models based on psychological hypotheses about the process by which a mind makes a decision. They could also be neuroscience models, but they are usually characterized by having much fewer parameters, and they're more interpretable. Right? So you put together pieces that individually have meaning, let's say encoding noise or some kind of decision rule and some attentional mechanism. Right? So these are designed to be interpretable. But the downside is that they're potentially not as powerful. So today we're just going to talk about process models. Bayesian models fall squarely into this second category. Everybody okay with that? All right, so other process models are signal detection theory, which you've probably heard of. Drift diffusion model is also a process model, very few parameters, hopefully interpretable components. And Bayesian is a special kind of process model. Now, what's special about Bayesian? So Bayesian models are suitable when you are considering decisions where the state of the world is unknown to the decision maker. So there's some form of uncertainty. And truth be told, it doesn't really matter where the uncertainty comes from. The Bayesian models are in principle equipped to handle all kinds of uncertainty. And the other characteristic is that there's some kind of optimization involved in Bayesian models, right? So the decision maker would maximize some kind of objective function. In many cases, that's actually just accuracy, like how well do you do on a task? How often do you get it right? And the core of Bayesian modeling that we're going to discuss today is of that nature, right? It's an observer who's confronted with uncertain information and just trying to get it right, to report correctly the state of the world. But it could also be more sophisticated objective functions, including like a reaching error, let's say in a motor task, or some kind of point rewards if you are more combining uncertainty with value, or at a very high level ecological scale, it would be survival. Now, there's another claim that's intertwined with these two aspects of Bayesian modeling, which is that the brain represents probability distributions. However, this claim can be set aside for the moment, and if we have time, we will talk about it. It is something that can easily be confused with the top two claims, but you don't have to buy into the third claim in order to be productive using Bayesian modeling, right? You can just think about those two bold-faced things without ever thinking about the representation of probability distributions, right? So here are some pictures of Bayesian models in recent papers, and the only message that I want you to take away from here is that it's obvious that these Bayesian models are process models. Why? Because they have boxes with arrows, okay? Boxes with arrows, well, that's that I think about is DNNs also have boxes with arrows, but these are more interpretable boxes with arrows, right? So every arrow has a concept with it, like a cognitive concept that hopefully generalizes across tasks. Now, why would you do Bayesian modeling? So there are many reasons to Bayesian modeling. So one is evolutionary or normative. So I mentioned to you that Bayesian models are designed to study some kind of optimal decision making, right? You're maximizing some objective function. And you can make the very strong claim that that's exactly what evolution has been doing for tasks that are important to survival. And those are often the perceptual tasks, perceptual motor tasks, sensory motor transformations. So you could make the plausible claim, which is very hard to verify, that for these very basic processes, the brain might actually be striving to the Bayesian ideal. Now, a more pragmatic view, which I honestly endorse a little bit more, which is that in practice, it turns out that these are good models for a wide range of behaviors. And then there's Bill Geisler's couch argument. I don't tell him that I'm call it like that. This is Bill Geisler. This is his couch. Actually, this is just a generic couch. But Bill Geist's couch argument is it is harder to come up with a good model sitting on your couch than to work out the Bayesian model. So this is the beauty of Bayesian modeling. If I give you the starting assumptions, you can just derive everything else without making additional assumptions. Now, in practice, there's always some fudging that you can do in order to account for processes that you're not modeling and they're capturing by the Bayesian model. But by and large, one of the strengths is that it's a fixed recipe, and we will be talking about this recipe, and by the end of the day, you'll be able to follow this recipe. So that means that if I put you in a new task, you don't have to think hard, oh, like, how shall I start it from scratch? You just have to walk through the steps and adapt them to your particular task. Right? So it is sort of a lazy modeler's argument. And here's my favorite argument through Bayesian modeling, because Bayesian models are often a good starting point for non-Bayesian models. Okay, so if you start with the Bayesian idea of optimizing something, then you have a very good benchmark, and then you can vary away from it in different directions. You can say, okay, what if this assumption is not right? What if people are unable to do this kind of computation? And you can have like a framework of components that you can manipulate component by component. Does this make sense? Right, so this is more Bayesian modeling as a framework for model generation. Right, so this is potentially the most powerful use of Bayesian models. Right, so if you came here with this deep skepticism, like are people optimal, you can let that go because people are not optimal. It's okay. But Bayesian models could still be useful to generate suboptimal models. Where does uncertainty come from? We mentioned uncertainty. Uncertainty can come various sources. Very broadly speaking, could be noise in the system, or ambiguity. So ambiguity may need a little bit more explanation. So I'm going to go to the second part, which shows some illusions that have to do with ambiguity. And don't worry about the PDF because we are not there yet. That's going to come a little bit later. So I'll first have you watch this interesting video. So there's dramatic music. This is, of course, a matter of great importance. All right, so this is a paper dragon. And what do you see? It seems to be following you, right? It seems to be following you as the camera turns. You can actually build this dragon yourself. There's a paper cutout if you just Google paper dragon illusion. So what this is a dragon with a hollow face, right? So it's you make a concave face, a hollow face. But most of you will not have noticed that. Who noticed and didn't already know that this had a hollow face? Okay, so you might have been picking up on very subtle cues, but most people would just perceive it as a regular face, right? So this illustrates something that can be explained by a Bayesian model. The hollow face illusion is a very old illusion. This is just a new variant of it. And why do we see this dragon or this hollow face as a regular face? So this is the right face here. I don't know if my pointer works. It doesn't. In the central right face probably also looks like it's a regular face to you. Now, why would you perceive it that way? If you give me one word, it's fine. Just shout it out. Yeah, surprise, right? So the likelihood is how well is this particular image explained by the hypothesis. So let's say you have two hypotheses, just to keep it simple. It's a convex face, convex, or concave face, like this, right? And the evidence, the sensory evidence, the image on your retina, is equally consistent with both. So let's say the likelihood, which is how probable is the retinal image. My verbs in this sentence are screwed up. If the hypothesis were true. So the hypothesis is convex and concave. That's the hypothesis your sensory system is building. And the likelihoods could be argued to be approximately equal. Now, the prior is how much you would expect this hypothesis based on your experiences. And most faces are convex, and therefore you would have a higher prior for convex faces. So the idea then is if you were to multiply them and you get a posterior, the posterior would be higher for convex faces. And the one part of the Bayesian hypothesis is that the hypothesis that your system is making that has the highest posterior probability is what you end up perceiving, right? So that if I just ask you what do you perceive in this situation, then you would report the convex face because that has the highest posterior probability. Now, here's a question for you. This illusion works really well with a camera, like we just saw. It also works well with one eye closed if you were to do this in real life. Why would it not work if you have both eyes open? Depth perception, right? So you have disambiguation based on your stereopsis, right? You have two slightly different images in both eyes. Right? So this is an example of ambiguity, where if you view a three-dimensional image with one eye, you have a two-dimensional projection of a three-dimensional object that's inherently ambiguous, right? So you cannot unambiguously decode that, like reconstruct the image, and priors are helpful to do that. Questions? Okay, this is another example from a category called anamorphic illusions. Who's heard that term before? Anamorphic illusions. Right, so it's these flat drawings that look 3D when viewed from one angle. Right, so this is what it really looks like. It's just a wall and the floor. And if you look at it from one angle, again with a camera or with a single eye, then it looks three-dimensional. Makes use of this exact same ambiguity and the exact same kinds of priors. Right, so where's the ambiguity? It's in this projection, 3D world to 2D retina. What role do priors play? Well, if it's more expected, then you would disambiguate by multiplying by this higher prior. And what happens if you view with two eyes? Well, the likelihood is going to dominate, is going to favor the true situation over the alternative. All right? This Necker cube. You've probably seen this before, right? The Necker cube can also be seen in two different ways. It can also be seen as hollow or convex or concave. This is also an example of a broader category of object perception that I just want to briefly illustrate. So if you see this image, it couldn't just be one of those two objects in the world. It could actually be a wide variety of objects, some of which you have a high prior, but then you also have a likelihood. So the likelihood would give you all the objects, let's say drawn as wireframes, that when projected onto the retina would give you that image. Right? So on the right side, you see here on the bottom the image that you just saw, and on the top you see the 3D objects that have that same image. Right? So that means that the likelihood is going to be 0 for a whole bunch of objects, and it's going to be really high for still a very large number of objects. Right? And then the prior is going to help you select those. So the prior is obviously high for some of those things, but the likelihood is very low for those things. Now, what are examples of priors? So convex faces are more common than concave ones. We talked about that. Priors could live at the object level. We just saw that. Like, for example, spheres and cube-like objects might be pretty common. Light usually comes from above, right? Light comes from above here. Light comes from above when you walk outside. That also gives rise to illusions and to disambiguation that's associated with those illusions. Slower speeds are more common. That's also pretty well established by now. Cardinal orientations, horizontal and vertical orientations, are more common than oblique orientations. And so there are lots of statistics that your brain could have picked up over a lifetime that could then influence your expectations in any given situation. Right? So that's the power of priors. So the take-home message from these illusions could be that they're not just bugs in the system, but they may be the product of the result of a product in the most literal sense, the result of an inference machine trying to do the right thing. So the right thing meaning combining the prior information as a likelihood. And wrong, quote-unquote, wrong percepts can often be traced back to a prior. Now, you may be tempted to say that Bayesian models are about priors. That's fake news, okay? Just drop that misconception right here and now. I don't want to hear that anymore. So what Bayesian models are about is the Bayesian decision maker making the best possible decision, so given that objective function. And that may or may not involve a prior. And as I said, you could extend this by the brain representing probability solution, but again, that may or may not involve a prior. So you might be very confused at this point, like how can you have Bayesian inferences without a prior? So let's move to a case that is going to illustrate that. So I would like you to now open exercises.pdf. I'm going to do that myself. And go to case 1, which starts on page 3. So it should look like this. Okay? All right, so I apparently screwed up the Wi-Fi password, so I'm going to, that might have been a cause of confusion. Apparently it's lowercase epic, Sana. I'm pretty sure I used uppercase earlier. This? All right. Okay, so
both username and password lowercase.
okay, both username and password lowercase. I don't know why I'm changing this because I'm putting up a different slide. Anyway, so if you're still starting with that, that's okay. I'm going to be talking for a little bit more before we actually start with that. All right. Okay, so here's another video for you to enjoy. Who knows this music video? All right, so if you don't know it yet, here's an important homework assignment. Go watch it after this tutorial because it's really cool. It has 43 illusions that were filmed in a single shot. They did 81 shots, but the last one, oh no, sorry, but they eventually chose the best from all those shots, but they had to film the entire sequence because everything depended on each other. It's super cool. Anyway, what kinds of illusions are these? Like, how would a perceptual psychologist describe the fact that you see a red triangle here, even though this is made up of different objects that are at different depths? What kind of phenomenon is this? Shout it out. Gestalt, right? So if you made the link to the exercise, you could have known that, right? So this is Gestalt. Now, Gestalt laws are descriptions that psychologists early in the 20th century came up with to describe the organization of our perceptual experience. So one law is the law of proximity. What do you see on the left? A bunch of disorganized little squares, right? What do you see on the right? You see a single cube that's made out of 3 by 3, right? A single square. So why is that? Well, the law of proximity would say spatial or temporal proximity of elements may induce the mind to perceive a collective entity. It's very comforting. So law of continuity. In this stimulus, anything that pops out to you? Anything salient here? Any snakes? Who sees this snake here? All right, great. Do you see it here? Yeah? All right. Okay, so first of all, you wouldn't survive if you were hiking right now. Number two is, once you see it, it's very hard to unsee. And third, this seems very natural to us when you actually see it, right? So you connect the pieces that are aligned with each other, and that's the law of continuity. Elements that are aligned tend to be grouped together, right? That's not a Gestalt law. Law of common fate. It's supposed to be moving. Why is it not moving? Oh. So what do you see here? Do you see 6 loose dots? Who sees 6 loose dots? Okay, if you raise your hand, I know a good neurologist. So who sees 2 groups of 3 dots that are moving up and down? Raise your hand. Okay, who was asleep? All right. So when elements move in the same direction, we tend to perceive them as a collective entity. That's the law of common fate. Now, the Gestalt principles have been criticized for being extremely made up sounding, right? They're not very precise. They're empirically driven. They do explain some things, but they don't really help us in every situation. And things like tend to and may are just a little bit too uncomfortable for somebody with a computational mindset. So we're going to study in case 1 a potential Bayesian account of Gestalt percepts. Okay, so now it's really the moment that we're going to turn to this page. So what you're seeing here is just a simplified variant of that stimulus that I just showed. So here we see 5 dots that you view as moving together down. So each of them is moving down. That's what I should say, right? So the traditional account is the Gestalt account. That's the law of common fate. But now we're going to follow a recipe that can lead us to a Bayesian account for the percept that you see them moving together. Now, what's the alternative account? Well, the alternative account is that, well, they are each moving independently, but they just happen to be moving all in the same direction. Does it make sense? Right? There are many other alternative accounts. Let's say 2 are tied together, and the other 3 happen to be moving in the same direction. Right? But we're just going to focus on 2 scenarios. Scenario 1, all dots are part of the same object, so they're connected, and they're therefore always move together. And to simplify the problem, we're not going to look at speed, we're just going to look at direction, and direction is only going to be up or down. So the probability is going to be 0.5 for each of those two possibilities. And scenario 2 is each dot is an object by itself. Each dot independently moves either up and down. Each is probability 0.5. And just by chance, they just happen to be moving all down. Is everybody clear on these two scenarios? Right? So the question to the perceiver, to you, is really which of these scenarios is the true one, right? It's ambiguous. You can never tell for sure, but if you're Bayesian, if your brain is Bayesian, you can still reason about these two possibilities. So what you're going to do now is going to this stepwise process. The first step in that process is to describe the process by which the state of the world, in this case, any of these scenarios, generates the observations. And the observation here is down, 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 down. Okay? Each dot is moving down. That's the summary of the observations. Right, so what I'd like you to do is get started with part A. Part A describes the two scenarios, and in the top of the box is the state of the world variable. Right. So in this scenario, what is out there in the world? In this scenario, what is out there in the world? Okay. And then in the bottom, you're going to put the observations, and the observations. They're going to be the retinal images, right? The retinal image of the dots moving down. So I1 to I5. The motion directions could be either a single motion direction if it's a single object, or 5 different motion directions. Okay, so who can tell me what I should put in this box? Can you raise your hand if you want to give that a try? So first of all, where would I put I1, I2, I3, I4, I5? So let's do this collectively because nobody wants to speak up among 300 people, I suppose. So just draw with your finger in the air where you would put I1 to I5. Okay, just draw it. Like, where would you put them? How are they organized? At the top or at the bottom? Who thinks at the top of the diagram? Who thinks at the bottom of the diagram? Good. And then would they go in on the left, on the right, or on both? Who thinks they go on the left only? Who thinks they go on the left or right only? Who thinks they go in both? Awesome. This is just a great group. So it would have I1, I2, I3, I4, I5, I1, I2, I3, I4, I5. Right? So in both scenarios, you have to explain the same observations. Right? So the observations, they're always going to be in the bottom of the diagram. There's nothing that goes from the observations to something else. The observation is just the endpoint of the generative process. And that's what your perceptual system takes as input. Okay, does this make sense? Right, so this is describing how the observations come about. Now, who wants to make a guess about the variable that goes in here? It's a single letter. Just say out that letter. What goes there? S, right. How did you get that? Well, by reading the text, a single motion direction. Right, and then in scenario 1, they move either together up or down, each is probability 0.5. Right, so in this diagram, you would have a single S here. And in this diagram, you would have S1, S2, S3, S4, S5. Does it make sense? Right, so the motion direction is up or down, but there's either a single one if it's a single object, or there are 5 different ones if there are 5 different objects. Yes? Questions? Okay. All right, so this is the interesting part. I'm going to give you a few moments to think about this. What are the likelihoods of scenario 1 and scenario 2? So the definition of likelihood is the probability of the observations. The observations, remind you, is down, 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 under scenario 1, and or under scenario 2. So these are 2 separate calculations. I want to hear 2 separate numbers, and you can think about this for a few minutes. I want this to be sort of discussion-based, so talk to the person next to you, and your TA is going to lead you through parts B, C, D, and E. Go ahead. All right, let's touch base briefly. Test, test. Can we get the sound back? Yeah. Test, test, test. All right. Likelihood of scenario 1, 0.5. Likelihood of scenario 2, 0.5 to the power of 5. Do the likelihoods sum to 1? No. Explain. 0.5 plus 1 over 32 is not 1. Now, the deeper explanation is that these are not actual probabilities, right? So these are likelihoods. And this relates to the phrase, part E, what's wrong with the phrase likelihood of observations? Well, this is important terminological detail. So in the language of inference, the likelihood is always the likelihood of a hypothesis, right? It's likely of an unknown state of the world. But to calculate that likelihood, you calculate what is the probability of the observations under that hypothesis, right? So the likelihood of the scenario, as it's stated here, is the probability of the sensory observations under that scenario. So that means that the observations are given, right? What enters your retina, it is what it is. What can you do? But your reasoning is about the underlying state of the world. So that's what you calculate the likelihood over. So if you want to distinguish yourself from people who have not taken this course, you will start correcting them when they say the likelihood of observation. Say, no, 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 no. It's the likelihood of the hypothesis. Everybody okay? And likelihoods do not sum to 1, right? So because it's the probability of the observations given the scenario. So if you were to sum over all the possible observations, you would get 1, but not if you take those two likelihoods. They can have any relationship with each other. All right, who has already, any questions on this? All right, who has moved on to part F? Can you raise your hand? Okay, what are the prior probabilities of scenarios 1 and 2? It's somewhere in the text probably. 2/3 and 1/3. All right, so I hope that that's not what I wrote. So what I intended to say is that the prior probabilities are, sorry, where did it say 2/3? Oh yeah, you're right, 2/3 and 1/3. Good. Sorry, yeah, 2/3 and 1/3. So the prior probabilities of scenario 1 and 2 are 2/3 and 1/3. So then we're going to move on to proto-posterior. So proto-posterior is a non-existent word. I made it up because I couldn't find what it's officially called. So if you want to embarrass me, just tell me what it's really called. But if you take the likelihood, you multiply it by the prior, but you do not normalize yet, then you get what I call proto-posterior. I call it proto-posterior because it's not quite a posterior yet. So what is the proto-posterior of scenario 1? It's 1/2 times 2/3, so it's 1/3. Okay? Who got that? Awesome. All right. So what is the proto-posterior of scenario 2? It's 1/3 times 1 over 32, right? So it's 1 over 96. Okay, who got that? Awesome, great. Do proto-posterior sum to 1? Who thinks yes? Who thinks no? Okay, no is right. Proto-posteriors do not sum up to 1. No reason to. But posteriors do have to sum up to 1. And so to achieve that, you divide each of the proto-posteriors by their sum. So who has already done that? Okay, could you tell me what you got? Yeah, you in the front row there. Yeah, yes. The actual posteriors, yeah. Yep. Yeah, so that sounds about right. I actually don't remember the answer. Who got that? So yeah, so the first number should be a very high number, right? It should be very close to 1. Any crowdsourced opinions here? Like, what do we get? 1.96, right? The second number should be 1 minus that. Okay. So why is that? Well, if you trace it back, what was much higher for scenario 1? The likelihood or the prior? Who thinks the likelihood was the thing that causes the posterior to be higher for scenario 1? Raise your hand. Who thinks that the prior is doing the work? Okay. Who's utterly confused at this point? Okay. Who's confused but doesn't want to admit it? All right. So if you look back, the likelihood of scenario 1 was 1 over 2. The likelihood of scenario 2 is 1 over 32. That's much smaller, right? So the likelihood is doing the work here. So even though the prior probability of scenario 1 is lower than the prior probability of scenario 2, it gets overruled by the likelihood. Okay, so that's why once you calculate the posteriors, you are getting a much higher posterior probability for scenario 1. Everybody okay with that? Any questions here? There's a question there. Yeah. In blue shirt? What was the, yeah. You have a question? All right, okay. Okay, yeah. That's right. No, so right now we are just considering those two scenarios, but as I had forgotten myself, I state here that scenario 1 occurs twice as often. So I actually got it wrong. So it's 2/3 and 1/3, right? But 2/3, 2-to-1 ratio is a much smaller ratio than 1/2 of 1/32, right? So in this case, the prior and likelihood both favor scenario 1, but the likelihood is doing all the work, right? So the priors are not that different. So you have just applied Bayes' rule, right? So who had never done Bayes' rule before? Okay, a few. Okay, so this is sort of initiation, right? Like your first steps, your first kiss, your first Bayes' rule. You take the likelihoods of the scenarios, you multiply by the priors, you get posteriors, you divide by their sum, you get two numbers that sum up to 1, or multiple numbers that sum up to 1. Those are the posterior probabilities. Now, in order to close that argument, you have to make some kind of prediction for what this observer is going to do. So, the standard Bayesian observer for discrete hypothesis states that the percept, the thing that you perceive, is the scenario with the highest posterior probability. Right? So that's called maximum a posteriori or MAP estimate. So sometimes there's a question what this a means. And that's Latin. A posteriori means like afterwards, together, right? So it's the maximum after you calculate the posterior, right? So after you take into account the observations. So as opposed to a priori. So the a here is actually not an abbreviation of anything, it's just a. So in this case, which scenario would be favored? Who thinks it's scenario 1 that's favored? Who thinks it's scenario 2 that's favored? Okay, scenario 1 is favored. Scenario 1 is favored both by the likelihood, by the prior. But, as we said, the likelihood is doing the work. So would it be consistent with the law of common fate? Right? The law of common fate, would that favor, in this situation, scenario 1 or scenario 2? Who thinks 1? Who thinks 2? All right, so scenario 1 is the answer. So scenario 1 is where everything moves together. It's a common fate. But what we've done now is, based on these likelihoods, we have argued that this is also, under a Bayesian line of reasoning, the most probable scenario, right? The idea here is that you would, if you were to consider scenario 2, every single one of those 5 objects just happens to be moving in the same direction, right? So that it would be a huge coincidence, right? So in my undergraduate class, we call this the "you gotta be shitting me" argument, right? You gotta be shitting me that all those 5 things are just moving in the same direction. It's much more parsimonious, it's much more it requires much fewer assumptions to think that it's a single object that just happens to be moving down. All right. So how does the Bayesian observer model complement or go beyond the traditional Gestalt account of this phenomenon? Any thoughts on that? Yeah. 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 This is a quantitative approach, right? So that means that you can now have you're making more commitments, right? So you can try to vary different things, such as the number of dots, or the amount of noise, or the strength of the prior, by creating expectations, and then you can get predictions for what would happen to the percept in those situations, right? And that's much harder if you just have this narrative description provided by Gestalt laws. All right. Note that in this case, like very often, the action is in the likelihood. The prior is relatively unimportant, right? So even though the prior in this case is 2-to-1, sorry for messing that up earlier, it is a much lower ratio than the ratio of 1/2 over 1/32. The interpretation of the likelihood is in terms of hypotheses, right? And each possible value of the world state is a hypothesis, and the likelihood of the hypothesis, the observers, apostrophe forgotten, that believe that observations would arise under that hypothesis. Priors and posteriors are similar belief distributions whose arguments are hypotheses. Right, so the word belief and degree of belief is something that you see a lot when people discuss Bayesian models, and that's because these are internal to the observer. So if you have an observer, the observer can build beliefs, rational beliefs about what the state of the world might have been, and that's captured by likelihood, prior, and posterior. Questions? All right, then we're going to move on to this. Yeah. 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 That's a great one. Yeah. But you can also then start making more sophisticated hypotheses, which is that there's one object and another object. Yeah. Okay. Yeah. Yeah, it depends on how complex you make that one object. Yes. So that's in the example that we saw earlier. Yeah, but I would see that as two objects. Yeah. All right. So let's continue with these slides. So the take-home message from case one: with likelihoods like these, who needs priors? So this is just to illustrate that in this case you can get an interesting principled explanation of Gestalt laws, and not just this particular Gestalt law. Many other Gestalt laws are of the same type, but the work is done by the likelihoods, not by the priors. Right? That doesn't mean that priors are generally not important. We saw some cases where they are important, but I don't want you to get the idea that Bayesian inference is just about priors. All right, if you want to know more about this example and examples like these and the slightly more formal treatment, you can check out this book. Case two, motion sickness. So before I go there, we had this discussion over brunch today. So it was about babies. So I have a baby, and babies cry, and sometimes you have to infer why a baby cries, right? So your baby can have tummy ache, or not want to sleep, or want to play, or just dislike you generally. All of those are categorically discrete scenarios that can give rise to the same observation, right? So we just saw an example of that at a very perceptual level. But this example is going to illustrate, for one thing, that you can also lift this to more abstract hypotheses. And we're going to also see an example of a competition between prior and likelihoods. So this is the most outrageous paper that I read in a long time. So this is by Michel Treisman, who was the husband of Anne Treisman, who you might know from theories of attention. This is the days where science papers could be 2 pages without data, and you could still get them published. Since the occurrence of vomiting, so that's already a great start, as a response to motion is both widespread and apparently disadvantageous, it presents a problem for evolutionary theory. A hypothesis is proposed suggesting that motion sickness is triggered by difficulties which arise in the programming of movements of the eyes or the head, when the relations between the spatial frameworks defined by the visual, vestibular, or proprioceptive inputs are repeatedly and unpredictably perturbed. Such perturbations may be produced by certain types of motions, or by disturbances in sensory input or motor control produced by ingested toxins. Here it gets really wild. So the last would be the important cause in nature, the main function of the emesis, how do you say that? Being to rid the individual of the ingested neurotoxins, right? So its occurrence in response to emotion would be an accidental byproduct of this system. So as far as I could tell, this is still the leading theory of motion sickness, despite any the absence of any empirical evidence. We're going to do this in case 2. So why don't you move to case 2, and we are going to talk about these high-level scenarios that, according to Michel Treisman, could be playing a role when your body decides that it has ingested toxins. Go ahead. All right. It looks like most people have already drawn the generative model. So the rules to keep in mind is the observations go in the bottom. Right? So both sets of observations are visual and vestibular. So I would draw one box at the bottom, visual and vestibular. And those are common to all 3 scenarios, just like in case 1. In scenario 1, the room is not moving, and you have a single node in the top, which is your motion in the room, and then 2 arrows pointing down. Do you have that? Second one is that your motion in the room and the room's motion together cause the vestibular observations, but only your motion in the room causes your visual observations, right? Because the vestibular observations are not affected by your motion. The visual observations are not affected by the room's motion in the world. And in scenario 3 is just that you have all the possible errors from the 2 causes, your motion in the room and ingested toxins, to the nodes in the bottom. Okay? So step 2 is the interesting part again, the inference. So, according to this hypothesis by Treisman, once in a while, a person might accidentally ingest toxins. So this has a small but non-zero probability. In previous 3, people would, of course, move around in the world, but surroundings would almost never move. So assuming, and this is a big assumption, that your innate prior probabilities are based on these prehistoric frequencies of events, draw a bar diagram to represent your prior probabilities of each of the scenarios above. Okay, so let's do that together. Scenario 1, would that have a high prior or a smallish prior or a 0 prior? We think high prior. That's sort of the default state, right? Scenario 2, would it have a high prior, a smallish prior, or a 0 prior, if you had to choose between those? 0, right? So the idea here is that would essentially never happen, that you have separate motion of the room in the world, so that the place where you're in is independently moving. And then scenario 3, according to Treisman's hypothesis, that would then have a smallish probability, right? So you would have high bar, 0 bar, and small bar. Yeah? For the prior. Okay, so now we're moving to the likelihoods. So the likelihoods have to do only with how well each scenario explains the hypotheses, explains the observations, right? So how expected are the observations? So under scenario 1, which is that it's just you moving, there's no room moving, how expected are these observations? Give me a number. Say it louder. 0, right? That could impossibly explain these observations, right? If you're just moving in the room in a regular scenario, you do not get this discrepancy between visual and vestibular observations. So the probability of the observations given the scenario is essentially 0, right? And that means that the likelihood of the scenario is 0. Questions? Let's move on then. So the likelihood of scenario 2. So if scenario 2 is the correct one, how expected are the visual observations? Are they 0? No, that definitely can happen. In fact, that's usually what happens when you're in a car or on a boat, right? You have 2 different motions, you in the room in the world, and together they produce the observations, and that can explain this discrepancy. Scenario 3, according to Treisman, according to Treisman, we already said it has a non-zero prior probability, but let's now talk about its likelihood. Could it explain the observations? Right, it can, right? So if you ingest toxins, then some toxins cause hallucinations, and some of those hallucinations take the form of discrepancy between visual and vestibular observations. So the likelihood would be 0, something, something. Now, which something is higher, I don't know. Okay, but they are both much, much higher than scenario 1. Okay, so here's the question for you now. If you have now 2 bar diagrams, prior and likelihood, and now you're going to multiply them to get posteriors. What happens to scenario 1 if you multiply them? 0. Why is it 0? Because the likelihood was 0, right? So it's a very common scenario, so the prior was high, but it's highly inconsistent with the observation, so the likelihood kills it. Scenario 2. What's the posterior of that? 0. Not because of the likelihood, but because of the prior, because in previous 3 this would never happen. So the only one that survives is the third one. So that's why you would believe in some situations that you have ingested toxins and then have this vomiting response to get rid of it. And so that's the Bayesian version of the treatment paper. Right? You can use numbers to illustrate it, but I won't bore you with that. It's the same idea. And so the percept here is your brain's interpretation of these scenarios, and it concludes that scenario 3 has the highest posterior probability and then acts upon it. Speaking of action, we're going to take a break until 1:30. See you in 15 minutes. All right, maybe if we just get started and people will approach the sound. Thank you for coming back. Thank you. All right. All right, take home messages for case 1, case 2. So we saw that likelihood and priors can compete with each other. Now, where priors come from is an interesting question. And it's a question that many people ask. So in this example, the priors came from evolution. And somehow they survived to the present and would still be applied now. Where else could priors come from? We briefly mentioned this earlier. Experience, right? So you have a lifetime of experience that things move slowly, that light comes from above, that phases are convex. Those are believed to be largely priors that are learned over a lifetime of experience. Are there any priors on an even shorter time scale? Instructions, right? So if you have a participant do an experiment and you're training them on a certain set of stimuli, they might use the statistics of the stimuli as a prior, right? So it is an interesting question without a general answer where priors come from. And priors are also really context dependent. So I just flew in from New York. I have been to a few restaurants now, and I look at the menus, and I look at the prices on the menus. And based on those prices on those menus, I expect very small portions because these are very low prices compared to New York. And then I get these huge plates. So my prior over like a price per gram of food was completely wrong because it's set in the New York context and it doesn't apply to the Lisbon context. Right? So this morning we had this discussion, like this €5 dish. Could that be maybe a small appetizer? No, it was actually a main dish. So that's a case where the priors really have to are very dependent on your context, and you have to be adaptive. All right, now that everybody's back, thank you for coming back. We continue with case 3, which is color perception. Color perception is really cool by itself. In case you didn't know that, we're going to talk a little bit about that. Anybody here who studies color perception in their research? Color perception? No one? Okay. So usually when you, in color perception, the main question is, what is the color of a particular surface? So that's the variable that's of interest. But then there's this other variable that plays a role, which is the color of the light, right? So this is yellowish light, and you can have a more white light if you walk outside, or you can have more blue light coming from your screens. And that's usually not the variable that you're interested in. And in computer science, such a variable is called a nuisance parameter. It's literally a nuisance in some cases, that you wish you knew the value of that parameter, but you don't. And the reason that that's a problem is because that parameter also will influence your observations. So in color perception, the most fundamental problem is that you have a color of a surface. This is probably the worst example because it's a transparent surface. A color of a surface, and you have a color of a light. The light reflects off the surface, enters your eye, and then produces some retinal image. The retinal image is what your brain has to work with to infer the color of the surface. But in order to do so, you have to make some assumptions about the color of the light. That is a Bayesian problem that we have so far not encountered. So the reason I'm putting this example is not just because color perception is so cool, but also because it gives us a new form of generative model, and you will learn how to deal with that. So to illustrate this problem, so look at this rendering of a cup. Who sees this as a uniformly blue cup. Can you raise your hand? Okay. So most people will see it as a uniformly blue cup. But what David Brainerd has done here is has picked out a few points on this surface in his image and looks at the retinal color of those points. And it varies widely from purple to gray to white to dark blue to light blue. Right, so if you were to zoom in, and I can do that here, but you can also do this at home, you can actually see that there's a lot of variation in the retinal color. So in the retinal observations are widely different, even though the object color itself is uniform. And the reason is, of course, that the illumination is different. In this case, not the color of the light, but the color of the light reflected off of other surfaces. So because this leftmost bottom surface is red, the light is reddish that hits that leftmost point, and that's why the retinal color is purple. Right, so when I asked you this question, what color is this mug, your brain was immediately doing that kind of inference. It was saying, well, it looks patchy with different colors, but those variations are all explained by variations in the illumination. Right, so you're automatically doing this inference where you take into account the nuisance parameter. Here's the opposite. So in this case, the retinal color is identical between A and B, but they're actually different. You perceive them as differently because you infer that one is in the shadow and the other one is not. Who has never seen this before, this picture? Okay, if you haven't, another homework problem, go do this. Just print out this picture, cut out A and B, and verify for yourself that they're actually the same shade of gray on the paper. Right? It's very hard to believe. I've seen this 100 times, but it's really hard to believe. If you're really good at focusing your attention on those two, maybe you can notice that they actually are the same shade of gray. But again, your brain is automatically doing the inference where it takes into account the color of the illumination, and in this case, infers that A and B truly have different colors because the illumination is different. Does that make sense? So this is a simplified version of the same one. So on the left, you see two gray squares that have the same color, but embedded in two bigger squares that have different colors. So who sees these two central squares as colored differently? Can you raise your hand? Who sees the central squares as colored differently? Right, I do too. So which one seems darker if you see them as different? The point with your finger, which one? That one, right? The right one seems darker. So the idea here is that the right one is interpreted by your brain as a dark patch in bright illumination and the left one as light patch in dim illumination. So Ted Adelson drew this picture where you pretty much have a shadow cast upon the left image, which makes everything retinally darker than it truly is, right? And the right one is not in the shadow, so you won't have that. So this is obviously not as convincing of an illusion as the previous picture that had much more context, but it conveys the idea that illumination influences color perception. So before we go to take-home messages, we're going to go to actually do this case. So go to case 3 in the exercises, which is called ambiguity from a nuisance parameter, surface shade perception. So even though I introduced this as a color perception problem, we're going to simplify this to a black and white problem, just because color has 3 channels and we don't want to bother with that. The idea is exactly the same though. So you have a shade of surface. Now it's a grayscale shade from white to black. So we're going to say black is 0 and white is 1. And you also have an intensity of illuminant, which also goes from 0 to 1. Okay? So surface shade and light intensity are the 2 world state variables. The thing that we're interested in as an observer is the shade of the surface. But the intensity of the illuminant influences your observations. And how does it do that? Let's assume through equation 1. So in equation 1 is a description of the generative model here, so that the retinal intensity, the amount of light that your photoreceptors measure, is a product of the surface shade, so the true color of the surface, and the light intensity, so how much incident light there is. So intuitively speaking, you could get the same color with a low intensity and a high brightness of the surface, or dim surface in brighter light. Does that make sense? Okay, so that's the intuition, and we're going to do this in the Bayesian context now. So the generative model is finished by now because we have specified the variables in this diagram, and that's all there is to step 1. So step 2 is the inference. So let's take each of these numbers to be between 0 and 1. I already said that. So for example, if the surface shade is 0.5, light intensity is 0.2, then the retinal intensity is 0.1, the product of these two. So now we're going to do the inverse problem. So the Bayesian observer is trying to infer surface shade, but light intensity is the other thing that plays a role here. So let's say that your retinal intensity is 0.2. And so that's your observation. Suppose further that you hypothesize the light intensity to be 1, which is very bright light. Okay, let's say daylight. Under that hypothesis, calculate what the surface shade must have been. Okay, so look at equation 1. Retinal intensity is 0.2, light intensity is 1. So what's the surface shade? Just shout it out. 0.2, okay? Now, suppose your retinal intensity is the same 0.2. So on the left-hand side, you still have 0.2. But now you have a different assumption about the light intensity. Now you say, oh, it's very dim light. Okay, so let's say light intensity is 0.4. What then is the surface shade? 0.5, right? Because 0.5 times 0.4 is 0.2. Everybody okay so far? Following along? All right, so let's now go to C. Explain why the retinal intensity provides ambiguous information about surface shade. Anyone who wants to summarize that for me? Awesome, right? So there are many combinations of those two variables that give the exact same retinal intensity. So based on the retinal intensity alone, you cannot reconstruct uniquely what was the surface shade and what was the light intensity. Right? You have one observation and two unknowns. That's pretty much what it is. So let's cast this now in terms of likelihood, right? So let's go with the same example. Retinal intensity is 0.2. That's your observation. And you can go through the same logic that we just did and map out a curve of all the possibilities in of light intensity and surface shade. In this diagram, you can just copy this diagram in your on paper or just draw in it in the PDF that are consistent with that retinal observation. Right? So what are the combinations of surface shade and light intensity that when multiplied give you 0.2? Right? So I'm going to ask you just to shade that curve in this diagram. Right? So this is not a regular function. Think of it as a 3D plot where the shading indicates that it's consistent with this retinal observation. Everybody okay with the question? Right? So what combinations of light intensity and surface shade would give you a retinal intensity of 0.2? I'll give you a few minutes to work on that. If you're done with that already, then you should just keep going. So E, F, G, and H. Right. Most people are pretty far along. Who has all three diagrams already? Can you raise your hand? Okay, great. So maybe you're ready to discuss this together. So the likelihood is going through those combinations that we just talked about. So what I want you to do is just take your finger and draw in the air the shape of the curve. 1, 2, go. Right, excellent. Good, you got it. The prior, now you need 2 fingers, okay? So same thing, what does the prior look like? 1, 2, go. All right, good. So the prior is going to be high between 0.2 and 0.4, regardless of the surface shade. It's just a prior over light intensity. Doesn't mean you don't have necessarily prior over surface shade, but that's what we assume in this problem. Okay, so the prior is high for it's something for in this band and 0 elsewhere. Now, for those of you who got to this part already, what happens to the posterior then? So the likelihood is going to be this curve that goes from here to here. Prior is this bend that is non-zero here. So the posterior, what it's going to do? All right, let's do this together again. 1, 2, go. All right. So the prior is just going to cut off part of the likelihood, right? Because the light intensities above 0.4 are impossible. So what does it mean for the surface shade? What surface shades are impossible? The surface shades that are lower than what value? 0.5. Why? Because if you look at what is the likelihood at a light intensity of 0.4, it's 0.5. We went through that. Right, so that means that the likelihood curve is going to be high, 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 but then this part is going to be cut off because the prior is 0. Right? So what you're left with here is a curve that goes from here to there. I think I can draw this, probably not like this, but you get the idea, right? It's going to look something like that. Okay? Who got that? Great, awesome. If you didn't get to that, do you understand it? Okay, any questions? Right. So then the question is, what would you perceive according to the Bayesian theory? Well, if you look at this diagram, there's still ambiguity, right? So it's actually really hard to say what you're going to perceive. It's going to be somewhere between 1 and 0.5, but it's not going to be somewhere between 0 and 0.5. Yeah? So what is going on here is that we had a prior over light intensity, which is our nuisance parameter. But in the end, that's going to influence our percept of the thing that we're interested in, which is surface shade. So the bigger message here is that in these problems where you have a variable of interest and you have a nuisance parameter that together give rise to observation, then a prior over the nuisance parameter is going to influence your percept of the variable that you're interested in, right? Now you could also have a prior over the thing that you're interested in, right? Then this diagram here is going to become more complicated, but I just want to illustrate that the assumptions that you as an observer would be making about the light intensity or the illumination would affect your percept of the variable of interest in the Bayesian theory. Is this clear? Okay. So then the take-home message here is exactly that. Uncertainty often arises from nuisance parameters. A Bayesian observer computes joint posterior over all variables, including the nuisance parameter. So you build beliefs over both illumination and surface shade. And the priors over the nuisance parameter matter for your percept. Okay. Here's a really nice example. So unless you've been living under a rock, then you know about the dress. The left part is the original image. So who sees the left part as white and gold? All right, who sees the left part as black and blue? All right, good. So this is it's like a deep rift in humanity, right? Like this greatly divides people. So the original was indeed black and blue, and it was overexposed. So if you correct the lighting is the color of the monitor is not great here, but you can see that the original colors are black and blue. It is believed that the individual differences in your percept of the surface colors arise from differences in the priors of illumination. And there's by now been several papers on this. If you're interested, you can look those up. But all of them have this Bayesian flavor where assumptions that you make about the color of the light in this picture would influence your percept of the colors of the dress. Any questions? Then we move to case number 4, which is sound localization. So, yeah. Yeah. No, so you could imagine that just by chance, this is a maximally ambiguous image, right? So you're really right on the border, and which way you're tilting is strongly determined by your prior. That's my best explanation. But yeah, I think people have also tried to, after this came out, have to try to deliberately create these super ambiguous images, and that turns out to be very difficult. So this sort of like an unexpected gift to color science, color vision science. Yeah. Right. Sound localization. All right. So what I'm going to do is take off this thing, and we're going to do a little experiment. Maybe I should not have done it right away. So I will be moving around. You'll be closing your eyes, and at some point, I'm going to say point. And the moment that I say point, you are just going to point your finger at where you think I am at that point. And you keep your hand like that, and you're just going to open your eyes. And don't cheat, right? So don't move your hand afterwards. Okay? Can I turn this off for a moment? All right. Everybody close their eyes. All right. How far off were you? Who was off by less than a centimeter? Who was off by maybe between 1 and 3 centimeters? Who was off by more than 3 centimeters? Okay, good. So this is a test of proprioception, and proprioception is noisy, right? Like all senses have some kind of noise. People have written large review papers about where the noise exactly comes from. We're not going to worry about that for the moment. Sensory observations are often noisy, and that's a source of uncertainty, and a Bayesian observer would have to deal with that. So that's the central concept that we're going to learn in this case. Right? So the sound localization is sort of our leading example, but it can be, you can think of this much more generally. So the generative model is as follows. So there are two nodes here. One is the variable of interest. In this case, the location of the sound. Okay? X is the noisy measurement. So the way that we're going to deal with noisy measurement is as living in the same space as the stimulus itself. What do I mean by that? If S is a location, X is also going to be a location. If S is a length, then X is a length. So think of this as, let's say, take a ruler and you measure the size of an object, then it's a noisy measurement of length. Now, if you come from neuroscience, then you would also want to think of the observation as some pattern of neuroactivity. So we're not going to do that right now. We're just going to abstract that and think of the measurement as living in the same space as the original stimulus. With me here? Right. So if S is a scalar, let's say position on a line, that's what we're going to do, then X is also position on the line. But if the true position is here, S is here, then X could be here or here or here. This is my interpretive dance part of the lecture. So we have to have probabilities over these, because that's what fully specifies a generative model. So we're going to say we have a distribution over sound locations, right? And that's going to become our prior, right? So in a world where speakers would do random shit, like they would say that they're going to jump off the stage and walk towards a place in the room, there's going to be a distribution of the places that they end up. That's probably what you were using as a prior right now, right? So in the time that I had, I would probably not have ended up all the way at the door. So P of S is a distribution of the world state, okay? But then we also need a distribution of the measurement. So we're going to talk about those two things. So the distribution of the world state, P of S, we're going to be assumed to be Gaussian. Why do we assume to be Gaussian? Because in practice, many distributions are sort of Gaussian, but most of all because it allows us to do some calculations in this example, right? So this left distribution is the distribution of the stimulus in the world. And that's going to become our prior, right? So this is the statistics that you've learned either through instruction or through exposure or through training. So we assume that the mean is 0 and the standard deviation is sigma s. Everybody okay with that? And the equation for the distribution is on top as a reminder for the Gaussian distribution, right? But now we also need the distribution of the measurement x. And we're going to assume another Gaussian for this. So we're going to think about these two Gaussians. So one is the distribution of S, and then the other one is the distribution of X around S, right? So if the true stimulus is S, then the measurement is going to be Gaussian, normally distributed around S with a different variance, sigma squared. Everybody with me so far? Okay. And I've illustrated that in this bottom right plot. If the true S is at the arrow, then the measurements are normally distributed around them. So if we have this picture, this completely specifies the generative model. This is all there is to know about step 1. Questions? So then we're going to the interesting part, which is the inference. So what you were just doing is you were reasoning based on a measurement x that your auditory system was making. And based on that x, you were trying to answer my question, which is, what is the location of the sound? So the thing that you were trying to infer was S, right? So the posterior that we are going to work towards is the probability of S given X, okay? What goes into that? Prior and likelihood. Prior, we get from that stimulus distribution, right? So the stimulus distribution gives us an expectation of where the sound location could be, even in the absence of any observations, okay? Now the likelihood, and this is an important one, right? So we're going to apply the same definition of likelihood. So the likelihood is the probability of your observation, the one that you were just having, under a hypothesis about the stimulus. So again, this is the likelihood of S, not the likelihood of X, right? It's the likelihood of the hypothesis. of the hypothesized state of the world. But in order to calculate that likelihood, you ask yourself, what is the probability of the observation under that hypothesis? So that's the probability of x observed given S. And I use this subscript observed just to make clear that this is a specific value of the measurement now. This is now not the generic random variable. This is a specific number. It could be 4.1, right? And you just had that number in your order tree system, and based on that, you were trying to build a belief over the stimulus. And the likelihood is one part of that belief, right? So you're asking yourself, could it have been this S? 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 And I have to stop, because otherwise I fall off the podium. So the probability of the observation differs based on these different S's, right? So if I was standing there and you have an observation that was close to there, then this particular S would have had a very low likelihood because it would have done a really poor job in explaining that measurement, okay? So that means that the likelihood also is going to be a Gaussian shape, but now look very carefully at the axis. So here, in the generative model, the measurement is on the x-axis because this describes what's the statistics of the measurements for a given stimulus. Now the axis changes. So the axis is now the hypothesized stimulus because that's what the observer is going to do. As an observer, you don't know what the stimulus is. That's the whole job, to infer what the stimulus is. So on the x-axis of the likelihood is a hypothesis. There's only one truth, but we don't know that truth. So it's still a hypothesized stimulus that you can build a belief about. Right? So the likelihood as a function of the hypothesis is given by that equation. So it's the same equation, but now you're flipping what is the argument and what is given. Here, you were given the stimulus, and you're interested in the distribution of the measurement. So this is part of the generative model. And here it's the opposite, and this is the observer part, where you observe a particular measurement, and you ask which of the hypothesized stimuli could it have been. Everybody gets the distinction here? So you have the exact same equation. So it's the same equation in the top here, x minus s squared. But the difference is now that x observed is the given. It's a particular number, let's say 4.1, and s is the variable. Whereas here, you're assuming a particular s, and x is the variable. From the point of view of the observer, observation is obviously always the given. Everybody okay with this? So even though you didn't do anything mathematically at this point, you made a big conceptual step. So the conceptual step is that you go from the measurement distribution, which is part of the generative model, to believe about the stimulus based on a particular measurement. That's the likelihood function. You use the same equation, but you flip what is given and what is unknown. It's probably the clearest way that I've ever explained this, so I hope you get it that way. All right, so now that you have those two, you can calculate the posterior. So the posterior is going to be this purple curve, right? So the likelihood is this blue curve, the prior is the red curve, and the posterior is the purple. I hope this is okay with people with color blindness. If not, complain to me afterwards. So the observation is x observed, that's the blue dot. And what you're doing when you're multiplying these two distributions is you're creating a new Gaussian distribution. And that's going to be the posterior, that's the purple curve. And here's already a little preview. Because the likelihood is so narrow, the posterior is going to look very much like the likelihood. And how can you understand that? Well, what if the prior was infinitely wide? It was like a uniform distribution, then it wouldn't do shit, right? You would just, posterior would be equal to the likelihood, okay? Now it's not infinitely wide, but it's still pretty wide. So it's going to shift the likelihood slightly over, but it's still going to not do that much. Everybody okay with this? All right. So right now, we have the framework in place to do case 5. So let's have a case 4. So let's have a quick look at this. So I explained the generative model. This is a stimulus distribution. That's P of S, equation 2. These are the two distributions, P of S and P of X given S, equation 2 and 3. Inference involves calculating the prior, which is just P of S, and the likelihood, which is L of S, which is P of X given S, but then with the arguments flipped. So that's all explained here. So if you followed me so far, you've pretty much gotten everything up to equation 7. Okay? So in equation 7, we have the posterior as the product of the prior and the likelihood with a proportionality sign. So the proportionality sign is a notational convenience. It's convenient because all it says is you have to normalize in the end, right? Because this is the same as you took the proto-posterior that we encountered earlier, and then at the end you have to make sure that probabilities add up to 1. So while I'm not doing that, I'm just going to write a proportionality sign. This is a reminder for me that in the end I have to normalize, but I don't have to worry about the normalization along the way. Okay, so this is a common thing. That's A. Okay, so what we're going to try to do now is we're going to numerically simulate this ourselves. Right? So what I'd like you to do is open MATLAB or Python, and we're going to create a figure similar to this one. So I'm going to do this with you so that we can save a little bit of time. All right, so you have to save it as something. All right, who is ready to code? Raise your hand. Okay, if not, better catch up quickly. Clear, close all. Right, you always start your code with that. So now let's create something that's very similar to this figure, figure 5. Okay, doesn't have to be exact, but let's do this. So the hypothesized stimulus is S hip, and it's a space from -10 to 10, let's say in steps of 0.01. Okay. Now the prior has a mean, so let's say mu equals 0, right? And sig s, which is the standard deviation of the prior, what shall we choose for that? 2. 2 seems reasonable, huh? Okay, mu is 0, sig s is 2. Everybody has that? And then do, let's say, sig equals 1. Okay? So that's the measurement noise. Sig s is the prior uncertainty, sig is the measurement noise. Now, since we're doing inference, we are going to have to use a particular observation, right? And x observed, in this case, well, just let's look at the picture. It looks like it's 3.2 or so. So let's set it to 3.2. Okay? Who's with me? Who has this? Can you raise your hand? Okay, great. So let's define the prior. So how do I define a normal distribution in MATLAB? Norm PDF. Norm PDF. What goes into the norm PDF? S hip, the hypothesis stimulus. What's the mean? Mu, and the standard deviation is sig s. So now we're going to, we have the prior. Right? All right, likelihood. What am I going to type here? Norm PDF again. So once you get to this stage of Bayesian modeling, the answer to every other question is normal distribution. So if you didn't pay attention, just that's sort of a very good guess. Norm PDF, what's the argument of the likelihood function? Same as hip. What's the mean of the likelihood function? X ops. Very good. TAs cannot participate in this, Lucy. All right, X ops is the observation. So the likelihood over the stimulus is centered at the measurement, at the observation. What's the standard deviation? Sig. Right, that's the measurement noise. Everybody okay this? If you're really anal, you can align the equal signs. All right, what's next? Posterior. Let's first do the proto-posterior. So actually, before I do that, I'm going to numerically normalize prior and likelihood. They are already normalized as probability densities, but because this is MATLAB, I want to numerically normalize them here. So I do prior equals prior divided by the sum of the prior. Right? That ensures that the prior sums up to 1. Right? Likelihood, in general, as we know, is not normalized, but in this case, it is normalized because of the shape of the normal distribution, the functional form of the normal distribution, so we do the same thing. This is just a technicality to bring them on the same scale in the plots. You can also continue working with densities, that's completely fine. All right, posterior, what I'm going to do first. This is not a trick question, just tell me what to do. Prior times likelihood. Prior star or prior dot star? Dot star, very good. Right, you point by point. Right, and then I normalize posterior. Right, posterior is always normalized. Right. What's not normalized? Zero point 0.0. Oh, it depends on whether you treat it as a density function or as a mass function. Yeah, so you could have everything divided by 0.01 if you like densities. It doesn't really matter. Yep. It particularly doesn't matter because I didn't put any numbers on the y-axis. But what's important here is that they are on the same scale. Right. Who's with me here? Can you raise your hand? Okay. Then what we're going to do is open a figure, and we're going to do a bunch of plots. So why don't we do figure hold on? Okay. And then we do plot. What's the type here? Let's first plot the prior. How do we plot the prior? As hip, prior, and let's plot that in red. Okay? And then we do the same thing for the likelihood in blue. And now we're going to plot the posterior in purple. And MATLAB doesn't have purple. Let's do it in black then. All right. Let's see if this code actually works. It will be a miracle. Oh. You sound so surprised that my code works. Who got this plot or something that looks like it? Raise your hand. Awesome. Good. So now you can play around with this. So let's say the prior, and actually in order to make it a little bit more visible, what I always do, and this is just me being anal, is default line width 3 or something, so that it creates thicker lines. It's more aesthetically pleasing. Okay, so let's play with sigma s. So I'm going to set sigma s to 0.5. So now the red curve is going to be very narrow. What do you expect? The posterior is going to shift over much more because the argument I was just making is that the narrower one is going to do the biggest job. So let's see what happens. And that's indeed what happens. So the posterior now is going to be influenced by the prior much more than by the likelihood. Everybody okay with that? Cool. So yeah, now that you have this basic code, you can play around with it. Now, of course, there's a reason that we assume these Gaussian distributions. And the reason is that we can actually do some math. So the posterior turns out to be a Gaussian distribution by itself. And I want you to spend a few minutes trying to figure out what the mean of that posterior is. Right? And to make that easier for you, I'm going to give you an auxiliary calculation which looks like a monster, and it is actually a monster. It's sort of one of those rites of passage that you have to do if you do Bayesian modeling. You have to complete the squares. And but I give you the final answer here. So if you multiply the prior, this part is going to be in the exponent. If you, and this part is going to be in the exponent as well from the likelihood, if you multiply the prior with the likelihood, right? So then this is going to give you this, right? So if you look at this expression, now tell me where I can see the likelihood, where I can see the mean and the variance of the posterior. How can I recognize that from this auxiliary calculation? Okay, so what I would like you to do is I would start with multiplying likelihood and prior. You get a product of two exponentials. You rewrite that in such a way that you can use this rule. And then you tell me how this gives me the answer to what the mean and the variance of the posterior are going to be. I'm going to give you a few minutes for that. If you finish with that, you can already continue with D. All right, let's touch base. How are you guys doing? Who got some understanding here? All right, that's good. So, well, actually, only a few people raised their hands, so that's not good. Maybe I didn't ask this very clearly, but what you end up with is that the prior is e to the power this. You multiply by the likelihood, which is e to the power this. If you have a product of two exponentials, it means it's e to the power the sum of those two exponents. So then you apply this thing. Now here's the trick. If you see something like this in the exponent, and the argument is s, then you can immediately read off what the mean and the variance are. Because the mean is the thing that's subtracted from s, and the variance is 1 over the thing that precedes it. If you look back to the general equation for a Gaussian distribution, it has s minus something squared over 2 times the variance. So look back here, s minus something squared divided by 2 times the variance. So that means that the mean is going to be this, and the variance is going to be 1 over that. Who followed me there? All right, good. So I encourage you to go through this math by yourself. This was just sort of to give you an impression, sort of just a quick story. But we are going to talk a little bit about this expression, because this expression, which I'm going to make big because it's important, is actually quite intuitive. So what this says is that the mean of the posterior is going to be a weighted combination of the observation and the mean of the prior. But the weights are given by the inverse variances. Sometimes Bayesian inference is called the church of 1 over sigma squared, and this is why, right? So observations get weighted by the inverse of the variance. So that means the more noisy you are, the less weight you give to the observation. So if sigma is bigger, the weight that you're giving to the observation is going to be smaller. The denominators make sure that the weights add up to 1, right? So this is a weighted combination, linear combination of the mean of the mean of the prior and the observation. So let's relate that back to the picture. So if you look at that picture, the purple dot, which is the mean of the posterior, is always in this model going to be in between 0, which is the mean of the prior, and the observation. However, where in between it is depends on the variance of the prior and the variance of the posterior. Whichever is smaller is going to attract the posterior more. So this corresponds to your intuition. Follow me there? All right. Now the variance of the posterior you can also read off, and it is this thing. Now, the thing that I would like you to take away from this is that 1 over the sigma squared of the posterior is 1 over the sigma squared of the measurement and 1 over the sigma squared of the prior. So that means that the 1 over sigma squared is always going to be higher after you after you combine the likelihood and prior, which means that the sigma squared itself is going to be smaller. So how do you see that in the picture? The purple is narrower than both the prior, those blue and the red, right? So this is a benefit that you're getting from combining likelihoods and prior. You're going to have more information. Okay, so what we've done now is giving you an intuition about this, show that the variance of the posterior is smaller than both the variance of the likelihood function and the variance of the prior distribution. So now we are ready to actually make a decision, because so far we've calculated the posterior distribution, but you actually have to make a report. If you think back to the experiment, you were actually pointing. That's the behavioral response. What is that going to be in the model? Well, it's going to be the mean of the posterior. So it's this expression that we just talked about for a minute. Right? So the Bayesian observer's response in this localization task is going to be the mean of the posterior. Okay? And as you can see, it integrates the likelihood and the prior. Good. Then now we're ready to move to step 3. If you say step 3, how come there's a step 3? That's because now we are going to make a prediction for a behavior experiment. So in the previous cases, there was no sensory noise. Now there's sensory noise. And what does that do? It causes this observation to be noisy. Right? And observation is in your observer's head. So that means that as an experimenter, you never know what X observed is. So that means that you can never predict S hat. However, you can still statistically predict S hat, and that's why you need step 3. Right? So because X observed is a random variable, it bequeaths, that's the word, right? It bequeaths its variability, its stochasticity upon S hat, right? So if X observed is a random variable across many trials for the same S, then S hat is going to be a random variable over many trials for the same S, right? So we're running a little bit low on time, so I'm going to just walk you through the logic there. So from trial to trial, your observation is going to vary, even though the same stimulus is presented to you every time. This is a fundamental property of almost every experiment that you do in psychology and neuroscience, right? That the internal measurement varies. I think I can stop doing this now. So for each measurement that you make, you're going to have an S hat, which is going to be influenced by the observation and by the prior, right? So each of the points where I'm standing now is going to give rise to an estimate, S hat. So that means that for the same stimulus that you present as an experiment over the course of many trials in your experiment, you're going to get different distributions, and you can calculate the distribution. You get different estimates, and you can calculate the distribution of those estimates. Yeah? So the purples here are the distribution, the posterior distributions across many trials, across 3 trials, with the same stimulus, right? So the posterior and the likelihood, do not think of them as a single thing. The likelihood and posterior are functions that differ from trial to trial because the underlying measurement differs from trial to trial. Conceptual issue that even published papers sometimes go wrong with this. Like likelihoods and priors in the presence of sensory noise will themselves be variable from trial to trial. Right, so the response probabilities are now obtained by applying this mapping X to S hat that we just talked about to X's that are drawn from the same S. So what you arrive at then is the distribution of S hat given S. And that could look something like this, where for the same stimulus, you can calculate the distribution of the estimate and compare that to your data. So that completes the Bayesian model in this case, right? So you do, even though as experimenter you do not have access to the measurement on a trial-by-trial basis, because it's in the head of your observer, you can still calculate its statistics, its mean and variance across many trials, and compare that to your experiment, right? So many of the Bayesian papers that test this theory have essentially calculated this distribution and then compared the mean and variance of this response distribution to those observed in humans, to measured in humans. Any questions here? So yeah, just to summarize that one point, the posterior exists on a single trial, but because the posterior is based on a noisy measurement, you never know exactly what the posterior is, and the best you can do in most cases is get the statistic of the posterior mean across many trials, because you can make a prediction for that distribution. Yep. That's right. Yep. 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 All right. So the question is, what if the prior and likelihood are way apart? And then the question is, should you still combine them in this way? And the answer is probably not. But that's a more general model. So the more general model would be that there is there might be two processes going on, where you have some process that generating observations, and there's another prior that is used on another proportion of trials. So something that's similar to that is causal inference, according 2007 +1. So I would check that out. It's a generalization of this kind of model. You would have to allow for the possibility of there being two generative processes. Take-home messages. Uncertainty doesn't just arise from ambiguity, like in previous cases, but also from measurement noise. Such noise is often modeled using a Gaussian. This has some theoretical reasons. Bayesian inference proceeds in 3 steps now, because the third step allows you to make a prediction, even though the second step is on a trial-by-trial basis. And the final result is predicted response distribution. Lots of people go wrong by confusing step 2 and step 3, because things are Gaussian and they sort of look like each other, so it's easy to confuse things. But if you want to avoid these mistakes, just go through the stepwise process. So in step 2, you calculate the posterior based on a given measurement. In step 3, you calculate the statistics of the readout, so the posterior mean estimate in this case, across many trials. And that does not involve a particular measurement anymore. Okay, so I want to talk briefly about change point detection. It's an important example. So what we just talked about in case 4 is sort of the workhorse of Bayesian models, and it's probably the kind of model that you've seen if you hear the talk about Bayesian models of perception. And there are many papers that test this theory. So Bayesian integration would be prior with a simple likelihood, like we dealt with. You can also do Q combination, which is that you have two likelihoods, let's say an auditory likelihood and visual likelihood. It's the same idea, largely the same calculation, right? And largely the same kinds of tests. There's an entire book on this. It's called sensory Q integration, and sort of half of the chapters there are Bayesian. What might be a little bit less well known, but often more interesting, is applying this Bayesian framework to more complex inference problems. For example, more complex categorization. So you have a category. The category has each category has a distribution, and each stimulus gives rise to noisy measurement, and you have to use the measurement to infer the category. Combining information across multiple items, that's visual search. Maybe surprising, you can also do that with a model that's using Bayesian inference. Combining information across multiple items and across a memory delay, which is change detection, can also be modeled using Bayesian inference. Inferring a changing world state. So if I do like this and I walk and I want to infer where I am and whether I'm close to the edge here, then I have to track my own position based on proprioceptive information, right? And because my own movement might be stochastic, this is a complex inference problem. Evidence accumulation across time. Learning, like how do you even get all that knowledge? How do you acquire the knowledge about the generative model? All of those can be treated in probabilistic terms, and often have been. And to just give you a taste of these slightly more complex examples, we're going to a relatively simple change point detection task. Who has heard of the notion of change point detection? Okay, so imagine that you're going to the same restaurant multiple times, and suddenly you notice that the quality of the food is substantially better. And that could be because the chef changed or the owner changed. Suppose you are a neurologist who wants to detect a seizure in a patient based on some physiological data, and you might not be able to get outward symptoms of the seizure, but you can still track those physiological measurements and try to figure out whether that singular event happened at one point. So those are change point detection, that there is a state of the world that changes, and it could change, for example, from one value to another fixed value. But because the measurements are often noisy, this is a hard inference problem. This could be a hard inference problem. So why don't we scroll to that problem, which is, it starts here. So change point detection is an example of hierarchical inference. Okay, so in this case, we are considering a situation where there is a time series of stimuli, S1 to St. So it could look like this. negative 1, negative 1, negative 1, negative 1, negative 1, negative 1, 1, 1, 1, 1, 1. Okay, so we're considering a time series of 10 points, and let's tell you that there's a change at one of these points. What does it mean to have a change? It means that before that, you have negative ones, and after that, and including that time point, you have a 1. So what is a t change in this example, B? Tell me what number is it? 7. 7. So 7 is the first time that it's a 1, by definition. Okay? I could also have it defined it as 6, but I'm defining it as 7, right? But now allow for the possibility that you have measurement noise, so that even though this is a true time series, this is the measured time series. So what I've assumed there is that every measurement is noisy. Right? And, let's assume for the sake of the argument that the noise is independent across the time points and normally distributed with the same variance. So that's equation 14 and 15 here. So independent across time points and normally distributed with the same variance. Okay? This is obviously an extremely simple form of change detection, but still it's not so obvious. Like if you just looked at this, sure, 7 could have been a change point, but 8 could have been a change point, and maybe even 9 could have been a change point, right? So we're now going to calculate the posterior over change point, right? So we need a prior. This is our prior, right? So 1 over t, each side change point is equally probable. Then this I already talked about. So now we're ready to do inference. Any questions about these equations? Right? Change point can occur with equal probability across each of the 10 points. Negative ones before, ones after. Each measurement is corrupted by Gaussian noise. So the inference is now calculating the posterior over change point given the time series of measurements. Okay? So we first do the usual thing, which is write it as a prior and a likelihood. This is no different than before. So the prior is constant, so we also observe that in the proportionality sign, so we get this thing. So the only thing that matters in this problem is the likelihood. So the likelihood is now over t change. The definition of the likelihood is the probability of the measurements, this wiggly time series, for a given hypothesized t change, right? This is so far just the same concept. But now we have a problem. What's the problem? Never in the generative model did I tell you what p of x given t change is. Right? So if I look back in step 1, I see x given s, I see s for a given t change, I see a p of t change, but I never see a p of x given t change. Okay? And if you look at the picture, it's obvious why. Because there is no direct arrow from t change to x. There is an underlying in-between state. There's an in-between state, an intermediate state, which is the true stimulus. Was it negative 1 or 1? Now, you're not actually interested in the true state. I asked you, when did it change? The time of the change. I didn't ask you what was the stimulus at a particular time point. So that means you have another example of A. What kind of variable was that? Nuisance parameter. It comes in a different guise now, but it's still a nuisance parameter. It's an unknown state of the world that influences the observations, but you are not interested in it. So the solution here is just like earlier, although I didn't really talk about it in those terms then, is something that's called marginalization. Okay? Who has heard the term marginalization? Okay, awesome, right? If you haven't heard of it, here's like the quickest crash course in marginalization that I can give you. Let's say you have 2 random variables, A and B, and they have a joint distribution P of A and B. But let's say I'm only interested in one of them. What do I do with the joint distribution? I sum over the other one to get the distribution over the first one, right? So probability of A is the sum of all possible values of B of probability of A and B. Now, probability of A and B can be written in a different way using this rule for conditional probability. So probability of A and B is equal to probability of A given B times the probability of B. Okay, so you get this equation after I substituted back in here. And now this is another example of marginalization, where you marginalize or you integrate over this other variable B. And the final step is that you can condition on everything on a yet another variable, which is c, right? And I write given c here and here and here, and then it's still mathematically correct. Okay, intuition. So this is probability calculus. What's the intuition? The intuition is that if there is a nuisance parameter, in this case b, and in this case it's s, the time series s, and you are not really interested in that parameter, what you do is you average over all its possibilities, right? So the probability of that possibility of b is here. So this is like the weight, and this is the probability of the thing that you're actually interested in, given an assumed value of b and c. Okay? So a Bayesian observer would never commit to a single value, even as an intermediate step. It would always maintain a probability distribution over every variable, including those nuisance parameters. Right? So and now I'm going to ask you to make the link. Right? So the likelihood of t change is going to be this equation. So tell me what is A, B, and C. So maybe let's start with C. What is C in equation 22? T change. What's B in equation 2? You have two choices. Who thinks it's X? Who thinks it's S? Right, it's S. S is the nuisance parameter here. So probability of S given T change. And so that leaves for A that it's X. Right? So we have applied rule 21, but we've done one more thing, which is that here it would say A given B and C. So it would be X given S and T change. But why can I leave out T change here? Any thoughts? Exactly, right? So if you know S, then you know the distribution of X. In fact, it's given by this equation. So once you know S, who cares what T change is, right? It doesn't change anything anymore. So you know that distribution. So this likelihood can be rewritten. We do not have time to go into that, so I will just leave this as something for you to by yourself. You get a likelihood over change point, and all that you need to calculate that likelihood is this time series of observations, right? And then this was an exercise to actually plot the posterior that results from that, and to read out the posterior. And then we can go through step 3 to calculate proportion correct as a function of several variables. Okay, so this is probably going to be possible for you to do by yourself when you get home, or if you care enough. But we won't have time to go over it right now. I do want to quickly ask you, how could our simple example be extended to cover more realistic cases of change point detection? There are many ways, so just name a few. Yep, right. So maybe the change point has more higher probability to occur in some times than others. Anything else? What other assumptions did we make that were not particularly realistic? Only one change point. Very good. There could be multiple. Anything else? Discrete time. That's often hard to avoid, unfortunately. Of course, you can have a finite time grid, but in many of these models, you have to assume a grid. And finally, one example is that other assumption that we made is that the stimulus itself could only take values -1 and 1, right? In a more realistic example, there is a change point, but both before and after the change point, there is variability in the stimulus itself, right? And you're not changing from one value to one value, but from one distribution to another distribution, right? If you want to see some real applications of change point detection, this is a good paper. Bob Wilson and Josh Gold have done a lot on change point detection, and then we have applied something very similar to detecting microsaccades from eye tracker data. Okay, so we're going to take a short break, 10 minutes. Try to be back here by 3 for the last part. All right, so it's already the last part of the tutorial. I want to briefly mention some Bayesian topics that I have not touched upon, and there won't be time to touch upon them. But I'm hoping that what we've covered so far will give you enough background that you can start reading those papers, right? So these are sort of extensions of the framework that we've described, and the core ideas are the same, but there are extra assumptions and extra components to the model. A relatively straightforward extra component is lapse rates and response noise, right? So far, we've assumed that the observer would report the maximum or the mean of the posterior. In reality, there might be some proportional size where you guess, or there could be response noise in your motor system. Something else that I haven't touched upon, but it's also really important, is utility and reward. So who here studies something related to value-based decision-making? Okay, quite a few people. So even though I haven't touched upon that here, it can often be combined with Bayesian inference. So it's very often the case that you have uncertainty about the state of the world, but you also have some interesting reward structure. For example, one correct answer is worth more points than another correct answer, right? Or you are having a graded dependence of reward on error. Okay, so in those kinds of situations, you have to combine Bayesian inference, is the calculation of posterior, with reward, and the place to start is then expected utility theory, right, where you combine uncertainty about the state of the world with different outcomes. Now, if you want to take that a step further, you would go to partially observable Markov decision processes. Who has heard of that term? Okay, so this also occurs a lot in neural data analysis. So the partially observable part is actually the least scary part of this term, because that's exactly what we have done today. Like we have had situations where there's a latent cause in the world, a latent variable that you're trying to infer. So that means that there's no direct observation of the process. And then what these processes also have is some time dependence. So you have a transition from one state to the next, which is essentially like the change point detection example that we just had, but it can be much more sophisticated, right? It could be the trajectory of a moving object, for example, that can have some complicated dynamics. And Markov refers to a particular property of that process. And then you can even attach different rewards to the different time points. So if you combine all of those things, then you have a partially observable Markov decision process. The math gets very hairy, but the concepts are pretty much the same as what we've covered today. Wrong beliefs. That's important. We all have wrong beliefs. Okay, insert favorite joke here. But wrong beliefs in a Bayesian context means that the observer who's doing the inference doesn't have the correct knowledge about the generative model. For example, when I came here and I had the prior over prices in restaurants, there was a mismatch prior to the reality here in Lisbon. So then that introduces errors of a different kind. So then there is a mismatch between step one, the generative model, and step two, the inference. Make sense? That's an important category of suboptimal models. So if you have your Bayesian optimal model and it doesn't quite fit the data, this might be one place to look. Maybe your observer doesn't have the beliefs that you assume that they have. Learning, I briefly touched upon that. So we assume that you have knowledge of those parts, those components of the generative model. But what if you have to acquire those over during training? And then you would actually have to infer the parameters of, let's say, the prior. So you have to build a belief distribution posterior over the mean of the prior, for example. Does that make sense? So it becomes hierarchical because of that. Approximate inference, super important. So in case 5, we already started talking about slightly more complicated forms of inference. If it gets even more complicated, sometimes in machine learning, it becomes really hard computationally. And then machine learners have often developed approximate inference techniques that give you about the right answer, but maybe with some deviation in some cases. And sometimes those algorithms can also serve as models for human or animal behavior. So it's another category of suboptimal models. Now, how the brain represents probability distributions. I mentioned that that's sort of a strong form of Bayesian inference, that you represent probability distribution over everything. And you can then link that to the neural basis. And we will not have much time to go over that, but I'm going to give you sort of my personal history with that topic. And there are many other researchers in the field who have worked on this. I started out as in my second postdoc working on implementing Bayesian inference with probabilistic population causes, a particular mapping from neuroactivity to probability distributions. And then we've tested some of those predictions over the years. We've also asked how can neural networks compute these things that you do in a Bayesian calculation. And my latest answer to that is sort of in this 2017 paper. And this preprint, it's not a published paper yet. In 2018 is probably the strongest test of the coding hypothesis. But I will leave this to you to delve into if you are interested. All right. So in our last session, I want to talk about model fitting and model comparison. Who's interested in these topics? Good. Otherwise, I would have just called it a day. Before I say that, I want to say something else, which is the exercises have answers. The answers are in a document. The document will be uploaded to the same places where you found the exercises. So if you were scrambling to write down the answers, don't worry, you did that all for nothing. You can read the answers in that document. But we just didn't want to give them too early. And that also allows you to do case 5 by yourself and check your answers. Model fitting and model comparison are topics that are not specific to Bayesian models, right? So these are things that every modeler has to struggle through sooner or later. So it's the bane of our existence. It's a source of many lost nights of sleep and frustrations and debugging and panic that you will ever finish your PhD, those kinds of things. Who has fitted a model in the last week? All right, good. So I'm hoping that some of what I'm going to say you don't know yet, but otherwise just bear with me. If you're fitting a model, one question is what do you want to minimize or maximize when you're fitting the parameters to the model? So the parameters of a Bayesian model are usually not that many. So if we think back to the case 4, the sound localization task, what there is a parameter that you would typically want to fit? Which symbol was that? Which parameter? If you don't remember, maybe I should just sort of go back here. Which variable here, which parameter here is unknown to the experimenter? Just say it out loud if you have a guess. Sigma. So S is unknown to the observer, but S is known to you as an experimenter because you present S, right? So sigma is the measurement noise of the observer, and that can depend on lots of things, right? If I take out my contacts, my sigma is going to increase by a lot. Maybe if I drink more coffee, my sigma is going to, I don't know what way it would go. Somebody should study that, the influence of coffee on sigma. Anyway, it's a free parameter, difference between individuals, you want to fit it. In that model, it was probably the only free parameter. In general, Bayesian models don't have a lot of parameters. That's one of the beauties. We're also going to talk about what fitting algorithms to use and then validating your fitting method. Does it sound like a reasonable agenda? Okay. What to minimize? So here's the first try. If you do linear regression, and this is sort of a quasi-physics example, like membrane potential as a function of current, right? So if you have these measurements, these are the dots, and you want to fit a line through it, then you would minimize the sum of the squares of the errors, right? But that's only a principled way of doing things if your model is linear. Otherwise, it's arbitrary and suboptimal. So it's not something that you want to do in general. The better try is to maximize the likelihood. Okay, now you might be confused because we talked about likelihood before. So let me explain what I mean this time. Output of step 3 is a prediction for the observer's response probabilities. Remember that? For example, in case 4, we had probability of S hat, the estimate, given S and sigma, right? So that means that if you give me a value of sigma and a particular trial where the stimulus was S, I should be able to run the Bayesian model and give you a prediction for the probability of every S hat, okay? Now, the observer is going to give you only one of those S hats, right? That's the observer's response. So what you're going to do then is you're going to plug in the observer's responses in that prediction. So that means that if it's a good prediction, then the observer's response is going to have a high probability. So if you can then define the likelihood of a parameter combination as the probability of the data set given a parameter combination. So now we're going to assume that all the trials in your experiment are independent. Big assumption, often wrong. Don't worry about it for now. And we write this as a big product. So we product over trials, where on every trial, I have a stimulus and I have a response. And I plug that stimulus and that response into the distribution that I got out of step 3. If you do not have a Bayesian model, you will still have a prediction, because that's the job of a model, to make a prediction for the mapping from stimulus to response. With me? So always there will be some kind of probability of response given stimulus and parameters. Now the parameters are supposedly intrinsic to the subject, so they are not going to be changing over trials. So the trials are labeled by I in this equation, but the parameter combination is not labeled by I. That's a common thing across all the trials. And what we're now interested in is the likelihood of the parameter combination. So the word likelihood you've encountered earlier in all of these examples, the likelihood was inside a Bayesian model, and it was the probability of the observer's measurement given the hypothesized world state. Okay, so now we are putting that all in a black box, which is your observer's head, and we are looking at the observer from experimenter's point of view, but we're applying the same logic, just the same way that the stimulus is unknown to the observer, the properties of the observer are unknown to the experimenter. So you see the metaphor here. It's not a metaphor, it's sort of an analogy, right? So the observer in a Bayesian model would calculate the likelihood of a hypothesized stimulus, but you as an experimenter would be calculating the likelihood of the observer's parameter, right? So it's stacked. And we could call that step 4. If you look back in that earlier slide, there's that has the 4 steps outlined. This is step 4, where as an experimenter, you're trying to infer the state of the observer. Now, you can also be all Bayesian about that, but the difference is that these parameters are often really unknown, and it's very difficult to put good priors on those parameters. Therefore, the state of the art in model fitting is still to fit the likelihood without assuming any priors over parameters. So I'm going to talk to you about maximum likelihood fitting without any priors. Any questions here? So the concept is just most important here, that the best possible way in a formal sense to fit parameters is to calculate the likelihood of each parameter combination. Okay? And now, how to actually fit? So the first try is just to search on a fine grid. So what I've plotted here for you is, in a simulated data set, the likelihood, in fact the log likelihood, as a function of sigma, which is this parameter that you want to infer about your observer. So what you do is you plug the data into this equation, you take the log, and you plot it as a function of sigma. So this is typically what a log likelihood function of a parameter could look like, with a single optimum, right? And what you see here is that that is a very reasonable guess of the observer's sigma, right? So if I ask you what was the sigma of this observer, this number is probably what you would respond, like 1.7 or so. Okay, and every other sigma would make the observed data extremely unexpected, extremely improbable. I would also want to add to you that if you apply this recipe to linear regression, it becomes equivalent to minimizing the sum of squares. So the maximum likelihood recipe is the much more general approach, but it reduces to minimizing the sum of squares in the case of linear regression. Now there are parameter trade-offs. So if you have more than one parameter, not just sigma, but maybe you have two parameters, then in many cases the likelihood becomes some relatively complex function of those two parameters. And as you can see here, the high log likelihood, the redder colors, is sort of a band, right? So there's many parameter combinations that fit approximately equally well. If you have a grid, you can plot this likelihood function. So now this is the heat map, right? The likelihood log likelihood is the color. And it's very often instructive to do that. Not necessarily because it's efficient, because it's not, but in order to see those trade-offs between parameters. So if you see something like this, you should get worried. You're probably already worried about other things, but you should get worried about this thing in particular, because it means that it suggests that the parameters are just hard to identify. You should have some more uncertainty about the parameters if there's this wide band of parameter combinations that fit approximately equally well. Now, I mentioned to you that the grid can be very inefficient. And why is that? Well, let's say I do a grid with 100 values per parameter. Then if I do a 2 by 2, so 2 parameters, it would be 100 times 100. If I have 3 parameters, it would be 100 times 100 times 100. And you can see how that adds up. It multiplies up very, very quickly, right? What's not a disadvantage of doing a grid search? Yeah, that's pretty much what I just said. It's slow because you have so many combinations to run through. Anything else? Say again? Yeah, it's also a waste of time because many of these parameter combinations might be really poor descriptors of the data. Anything else? Yep. Yeah. So you will never be able to find a value in between your grid points, right? By definition. Okay. So the better thing to do is using a built-in optimization algorithm, such as MinConf and MinSearch in MATLAB. So who uses one of those on a regular basis? Okay, great. Anybody using something similar in Python? Okay, great. What is it actually called in Python? I don't know. Okay, all right. I didn't hear any of that, but I'm sure we can look it up. All right, so let's see what that looks like. So here is one of those functions that have this trade-off. It's called the banana function because it looks like a banana. And here, all of these algorithms, they are minimizing something. So you could be minimizing the negative log likelihood in order to maximize the log likelihood, right? So here you're trying to find the lowest point in this valley. And what you see here in yellow is the tries of the algorithm, right? So it walks down to the valley, and then it spends some time there, and it goes in a different direction. It keeps going. Oh, it's getting close. The red is the real minimum. And eventually it gets there. Breathtaking. So the error is in the plot above, and it just goes down very gradually. Then like you can play this on a loop, and all is good in the world. All right. There are deficiencies to this algorithm. So as you can see, it is relatively slow in some cases, and this is a relatively hard optimization problem. The other thing is that it just goes into in these line patterns, right? It just finds the next point in the vicinity of its previous point, right? That's a common mechanism of many of these algorithms. They climb down the hill, right? So you go down the gradient. But sometimes that's not the best. And I had this postdoc in my lab, Luigi Acerbi, who's now with Alex Puget in Geneva, and he developed a algorithm that works for more complex inference problems. Inference for parameter fitting problems. So I'm going to show you how that algorithm does in this exact same problem. So what you see here, it explores a much wider space, and it hits upon the maximum, minimum much quicker, and that's it. So the way that it does this is by combining wider exploration with an estimation of the shape of the landscape. That's where the Bayesian part comes in. You're estimating the shape of this banana, and then it means that you don't have just the local information of the gradient, but you have some idea of what would be the next most informative point. Does that make sense? So this is freely available with good documentation. You can just go to this website to download this. So if you have a problem where your likelihood function is pretty complicated and you don't trust your fmin-con fmin search, or you have to calculate your likelihood functions through numerical simulation, I would recommend that you also try this, at least as a sanity check, so that you trust your fmin-con a little bit better. But maybe you're so happy with it that you want to stick with it. Okay? So if you have these three tools in your toolkit, grid search for very simple problems and for visualization, fmin-con fmin search for relatively easy tractable problems, and BAT for more complicated problems, then I think you can make a career in this field. In fact, in other words, I actually don't know any other algorithms, and I'm still reasonably happy. Huh? Sorry, what? Gradient descent. So there are many other fitting algorithms, and Luigi, in his paper on BAT, compared, I think, 20 different algorithms or so, and BAT does quite well compared to the existing algorithms. But yeah, this is not a gradient-based algorithm. All right, validating your method. So whatever method you do to fit your parameters, it's useful to do parameter recovery to detect obvious failures of your algorithm, but also to detect bugs in your code, which is always something to worry about. So this is an example from Jen, actually, who's one of the TAs here. So what she did here is she simulated data from her model using different combinations of parameters. So the input is a value of the parameter, and then there's different parameters that are the titles of these plots. And then the y value is the recovered parameter, which is what your algorithm returns. So if your code is bug-free and your algorithm is reasonably good, then you would expect some clustering around the diagonal here. In most cases, it's the case here in the bottom right. Maybe it's not so good, and you have to wonder why. Is it just because the problem is hard, or because there's something wrong in the code? Yeah, it's a useful trick. So model fitting. If you can maximize the likelihood of the parameters rather than any other objective function, do not minimize square error, bad idea. Do not fit summary statistics. So sometimes people summarize the data first and then fit the summaries. Sometimes that's necessary to do, but if it's not necessary, don't do it. The raw data will provide you more information about your parameters. Use more than one algorithm. So I would recommend a bit of paranoia here. Every fitting algorithm has its drawbacks. Those drawbacks are usually of different natures. So if you want to be more confident about your fitting results, just do more than one algorithm, and at least in some cases, and make sure that it's consistent. Okay? And then consider BATs when you don't trust fmin-con or fmin search. Multi-start is another useful trick. Many of these algorithms have to be initialized somehow, including BATs, and it's good to randomize your initializations to make sure that it doesn't matter. Yeah? Who's doing that already? Okay, good. Some algorithms allow you to do it automatically, and parameter recovery. Questions about model fitting before we go on? Okay, yeah. Yeah, so yeah, with some data sets, it's necessary to summarize first, because otherwise it gets computationally too difficult, or because you have to make too many extra assumptions, and that might be one of those examples. But if you're even if you're interested in only the summary, it is still often better that you make a model of your raw data and fit that model, then first reduce the data to the summary statistics, right? Because you essentially are doing like a two-step optimization where you first summarize and then you fit, as opposed to a single-step optimization that uses all the information. But a good counter-argument is that might be computationally too costly, or that you have to make too many extra assumptions. More model fitting. All right, so then model comparison, we get to different aspects of model comparison. So who has compared models in the past week? In the past month? Ever? Okay, all right, good. Model comparison is an important skill that sort of is related to model fitting. One big question that comes up is what metric do you use? So the first try is the visual similarity to the data. So here are 6 different models to the same data. The data are the points. The model fits are the shaded areas, and you just look at it, and you can already see that in this case, this leftmost model is the best. Don't underestimate this. Just looking at it, looking at the fit is just a very important part of model comparison. Of course, eventually you want to do something more quantitative, but very often just visual inspection gives you some information. So R squared is a common one. Just don't do it, unless you have only linear model, which almost never happens. Try number 3 is likelihood-based methods. So you already have likelihoods from the model fitting part, and that's good. And the problem is that you have to then use those likelihoods in some way to compare models. And then that's where it gets tricky. So you can do AIC, AICC, BIC, WIC, AIC, DIC, k-fold cross-validation, leave-one out cross-validation, log marginal likelihood. So even in my lab, there's already a wide diversity in the methods that people prefer. Now, there's actually some order to that chaos. So there are some metrics that are based on maximum likelihood, AIC, BIC, and there are metrics that are based on the full likelihood function. So they don't even require you to fit that single best priority combination, but they do something more sophisticated. Cross-validation can be either. Who uses cross-validation as default? Yeah, that's fine. You're probably in good shape. Now you can also split these metrics by what they actually are trying to optimize for. So there are some metrics that are judging a model by its explanatory power of the existing data. So how well are the current data being explained? BIC and marginal likelihoods, base factors, they fall in that category. There's also a category of metrics that really emphasize the out-of-sample prediction. And cross-validation is, of course, the main example of that category, but AIC and WAIC are actually approximations to that. So they also have very different philosophy behind them. And you can spend a lifetime thinking about the details here, so I'm not going to do that. I just want you to be aware of these different metrics and how they divide. Practical considerations, no metric is always unbiased for finite data, right? So you just like with model fitting algorithms, model comparison metrics, you should all take with a grain of salt. For example, AIC tends to under-penalize, BIC tends to over-penalize. So do not trust conclusions that are metric dependent. So my best advice is to decide in advance on a set of metrics that you're going to use, and then only be confident about your results if all the metrics return the same answer, that let's say model A is better than model B. If it doesn't, then yeah, you have to start asking hard questions, and maybe you actually have to conclude that your experiment is inconclusive, which is painful, but yeah, life is pain. All right, so this is what we can get out of these kinds of comparisons, right? Here we're using AICC and BIC and log marginal likelihood, and then we are calculating the mean and SEM across subjects of the metric for different models and different subjects. All right, so your model comparison metric and how you compute it might have issues. So how would you validate it? Well, model recovery. Model recovery is like parameter recovery, but now what you would do is you would generate data from each of those models, and then you fit each of those models. And then you see whether the right model wins for the right data set, for the corresponding data set. Right? Because you can simulate data from the model, you know the ground truth, so you can just compare it to the ground truth. Right? And definitely it's not going to go well all the time, but overall you would want to see that the model that generates the data is best fitted by that corresponding model. Right? So in this case, the diagonal fit should be best. It doesn't matter what the models are in this case. Here's another way to represent this. So the generating models now are on the x-axis, the fitted models on the y-axis, and the delta ASC, which is a measure of the badness of fit, is the color code. So that means that the white diagonal means that on average the best model is the model that generates the data. This is you can argue about how useful this is, but I find it useful at least to make sure that your code is working properly, which is always a concern. All right. And now, how would you avoid handpicking models? So this is a tricky issue. I just want to point out one answer, which is factorial model comparison. So very often these models, including Bayesian models, they have different components. These are different knobs that you can manipulate, and you can swap them out for other components, right? So for example, I have a Bayesian decision rule, which is what we derive today. But what if you're interested in comparing against another decision rule? Then you swap out the decision rule. But what if you also want to swap out your model of the measurement noise? Then that's another component. So each component in principle has many values, and if you want to combine all those values with each other across the components, then you end up with a factorial model comparison. So this is similar to factorial design of experiments, so you can mix and match moving parts. It's also a little bit similar to stepwise regression. So here are a few papers that have done factorial model comparison, and then you get just a big model space where each model is a particular mix of the different components. Does it make sense? That is a way to be sort of maximally agnostic about how you construct your models. I just test everything. My students hate me for this, but yeah, that's another question. So this is an example of how that could work. Right? You have 2 dimensions, 2 components. Each component can take different values, levels, and you factorially combine them. This is why my students would hate me, because you get very, very many models, and sometimes those models are very hard to distinguish from each other. Now, the fact that they're hard to distinguish, that is not a problem with the method. The method just brings that out. Because if you had just subselected a few models, you would maybe have had an easier time distinguish these models, but it would have been slightly disingenuous because you would not have tested other potentially promising models, right? So if you do this method of factorial model comparison, you will have to live with more uncertainty about what the best model is, but you can be more confident about rejecting many other models. That's often the story. Now, the best model might not always be a good model, right? So maybe all models are poor. So it's also useful to think about absolute goodness of fit. Who worries about that occasionally? Okay, so do worry about that. It's a good thing to worry about. So absolute goodness of fit is also sometimes just verified by visual inspection, right? So if you have data and for different subjects, that's the top row here, and you see that the optimal model does well for all of these subjects, and it sort of visually looks alike, then it gives you a little bit more confidence that this is the best model is actually a good model. You can be more quantitative, calculate something like deviance. Who has heard of deviance? Okay, so deviance is a statistical measure of absolute goodness of fit. Negative entropy is similar. And they pretty much ask you what is the irreducible variance, the unexplainable variance in the data, and how close does the model come in the limit that's set by that unexplainable variance. So I think in fMRI it's called noise ceiling, right? There's another challenge. What if different subjects follow different models? Right? This is always a concern, that you might have a heterogeneity in the population. There are methods for that, and our favorite method is hierarchical model selection, Klaas and Stefan and Carl Fristen have been working on this. These are the papers, and these methods, MATLAB code is available on their website. Returns the probability that each model is the most common one in the population, as well as the posterior probability for each model. So these methods have flaws, but they're the best available that we have now. So the take-home message of a model comparison, there are many metrics. So my recommendation is to do a specialized lab meeting or a reading lab on them so that you have some idea of this zoo of metrics and what their pros and cons are. And do due diligence to prevent your conclusions from being metric dependent. It's just very pragmatic. Do model recovery, consider doing factorial model comparison, quantify absolute goodness of fit if at all possible, and do a hierarchical model selection if you're worried about heterogeneity in the population. Okay? Any questions? Okay. So then we get to the last part, which is critiques of Bayesian modeling. All right. So this is intentionally left blank, and not because I don't have any critiques, but I know you have a lot of critiques, so we're going to fill this out together. All right. I've talked to you about Bayesian models in general and in a few specific examples. What objections do you have to this entire research agenda? Yep. Work in the assumptions. What for example? Yeah. Give me one example of such an assumption. Okay, I'll get back to you so that I have a better understanding of what you mean. Anything else? Prior is very? Yeah, prior is hard to get. I'm first going to collect your comments and then we talk about them. I'm anticipating a lot, so I'm going to decrease the font size. All right, so now you better start it with this list. Inference intractable. Is that a question or? So I'm just going to write down behavior might not be Bayesian. All right, anything else? Yeah. Yeah, so hard to apply to neural data or to make connection to neural representation. Yeah. Okay. Yep. In the representation as in yeah. Okay. Yep. 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 So let's talk about these for a moment. Behavior might not be Bayesian, so that's probably the easiest to deal with because I agree, but you don't know that in advance. So you were asking that, or yeah? So I would just say that's an empirical question. So I completely agree that in many cases it's not Bayesian, but you won't know until you try. Inference is intractable. We already touched upon that. This is very true. So if you do slightly more complicated cases, for example, Jen's project is about clustering, and in clustering you have many observations, and you have to decide which cluster do the observations belong to. Then exact Bayesian inference becomes a really complicated computation. It's at least computationally demanding for a computer. So you could make the argument that it's hard for the brain as well. And then you might have reason to look for more approximate algorithms. That's related to Emmanuel's comment about scaling to large data sets. So Bayesian inference often has trouble scaling to large data sets. So I'm going to reinterpret that question in terms of the behavioral tasks that we've been talking about. These are extremely simple behavioral tasks. Right? If you are crossing the street when you walk out now, you're doing a much more complex task with much more complex stimuli and much richer behavioral repertoire. And I just don't know if Bayesian models can help you in any way there. There have been some attempts, for example, Bayesian predictions for eye movements, but it's incredibly difficult. So that is a real big limitation. So I'm going to boldface both of these because I don't have a good answer to that. I don't think the field does. Hard to apply to neural data, make connection to neural representation. Yes, I also agree with that. But people are working on that. So I don't know, Ralph Hefner was here a moment ago. I don't see him now, but he's one person who's trying to make that connection, to make Bayesian models also work at the level of neural representations and neural operations. And the approaches that I listed in these papers, they also go some way to answering that. Now, there you can, there's now an interesting debate to be had about what can you learn about neural representations by starting with a abstract cognitive model such as a Bayesian model versus by training a deep neural network. And maybe the world shall meet somewhere in between at some point. But these are currently very different philosophies. So Bayesian cognitive models start with low dimensional representations, few assumptions, huge simplification, and the deep neural networks, they just throw any computational power that you have at it and then analyze the emergent representations. So the Bayesian models all feel more top-down in an epistemological sense than deep neural networks. And I think we're actually not sure how these two approaches relate to each other. Prior is hard to get, that's definitely true. So I talked about where the prior could come from. The easiest situation, if you just train the hell out of your subject and so that you can you can reasonably assume that they have the prior that you want them to have in your experiment. Even that approach is not foolproof because maybe they refuse to learn what you want to teach them. Or maybe the environmental priors that they've lived with for a much longer time than they've been in your experiment might play a role in their judgments. So it's often hard to control that. But the least you can do is not give this prior too much expressive power. So if you put a lot of free parameters in your prior, the entire power of the Bayesian framework becomes questionable because then you might as well train a neural network, right? The power comes from that you have relatively principled assumptions about where the different ingredients come from. And the prior is one of those ingredients. And the experimental statistics or natural statistics are two reasonable principal assumptions that you could argue the prior originates from. Okay, but it always requires some thought, and you have to be careful not to tweak too much post hoc. And if you tweak post hoc, just be honest about it. Say, my original assumption of a prior doesn't work. Maybe people have a different prior. Let's now try that. And that's legitimate. Parametric assumption distributions, that's a good one. We've assumed Gaussian distribution without very strong justification, but this is also one of those things that you can actually do model comparison on. So if you have a reasonable alternative model about the shape of the distribution, you just compare. Learning the structure of the Bayesian model, that's a really deep question. So if you have a baby like I do, and you're trying to figure out how it's actually learning to do inference, an important part is to actually learn the structure of these generative models. And there are theories, Bayesian and non-Bayesian theories, about how children, infants, or developing brains would learn the structure of generative models. One paper I can recommend is by Brendan Lake and Josh Tenenbaum. It's probabilistic program generation, and it's sort of an all-the-way Bayesian approach to learning from very few examples. Weirdness distribution is similar to this probably. Dynamics, so yeah, I think that's a bit of a mixed bag because in principle the Bayesian models can be adapted to dynamics, like we've already started looking at in case 5. But also I think that it's been much less tested in those settings. And I think that's an interesting open direction. Right. So that now that we've discussed this, let's see if there's anything else came up. Yep. Yeah. So in the examples that I sketched to you, the distribution assumptions were largely given by the experiment, right? So for example, in the sound localization experiment, if you were to actually do this in the lab, you would control the stimulus distribution. And our approach would then be to just train the subject extensively on that distribution so that you can reasonably assume that that's the distribution that they have in their head, and you don't have to make any additional assumptions on top of that, at least not in first pass. It's very difficult to make, to construct these generative models in a vacuum, and very often you don't have to. So you either have stimulus statistics or natural statistics to go by. But in a broader sense, it's much harder. So for example, also Josh Tenenbaum has work on structure learning, where you learn how different concepts relate to each other. So you learn that animal species are organized in some kind of tree structure, whereas cities on a map are organized in two-dimensional space. And those are two very different ways of producing data. And those kinds of structures also have to be learned. And that's a much, much bigger space, of course. And their approach to resolving that is by breaking it down into modules and then to compose those different modules. So then you can do learning on the compositions of those basic building blocks. So it is possible, and in fact, it's very likely that as a child learns, they have very strong priors about the kinds of structures of observations that could emerge in the world, statistical structures of the world. But I think a lot more work needs to be done to understand that structure learning. Yeah. Yeah. So you would ideally have a specific hypothesis about the non-Bayesian way in which it might be happening. For example, I derived to you for your Bayesian decision rules in the various tasks. You could have some kind of non-Bayesian decision rule, right? Where, let's say, maybe your rule is people ignore prior information, they just make a maximum likelihood estimate, right? That could be an alternative theory. And then you can compare those theories, and then you can just conclude that they're not Bayesian in this task in this very specific way. If you ask the generic question, are people non-Bayesian, or do they deviate from the Bayesian ideal? That's a harder question to answer, because then it then the question becomes how much deviation between the model and the data do you tolerate, and that's a bit arbitrary. So my best recommendation is to precisely formulate the alternative hypothesis and then compare the models. Yeah. Yeah. So yeah. Yeah, that's true. So I have to be a little bit more precise there. So if you have prior information that's useful for the task, then the optimal Bayesian observer would be using it. And if you would not be using that information, then you're still in sort of the broader Bayesian category. However, you would essentially be like having wrong beliefs about the prior. So that's one way to think about it, that you assume that the prior is flat rather than whatever it is. So yeah, then it becomes a matter of semantics whether you still call that Bayesian. But yeah, the optimal Bayesian model would literally use all the information that's in the generative model. Otherwise, it would not be maximizing accuracy. Anything else? Okay, so a quick poll here. So after this tutorial, oh, you have more questions, right? Yes. Yeah. 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 So two parts to that answer. So you are now representing the process of learning the optimal solution as something that plays out over time. So that is often reasonable, but it's very difficult to actually get at that learning process. So you don't know if that's happening across a lifetime, in which case you might actually have already much of that optimal machinery inside your head right now, or that you have to learn it on a case-by-case basis, which is probably more intensive. So it's actually difficult to test exactly like how far along that learning process you are. But the broader point that you're making, I completely agree with, that very often the brain would not necessarily find the optimal solution, but something that's good enough, especially when there is some kind of cost to the optimal solution. And there's these days lots of theories about resource rationality, like Tom Griffiths is one of the leaders there, where you are taking the optimal solution, the Bayesian solution, but you're also building in implementational costs at various levels. And then you can define a new rational objective to maximize. And very often what he finds is that you end up with algorithms that can explain interesting biases in human behavior if you assume this kind of this bounded rationality. Anything else? Cool. So who here came into this tutorial knowing almost nothing about the things that I ended up talking about? All right. So do you feel a little bit better about things now? Like, does this give you sort of a basis to think about? All right. Who here has heard something that they could apply to their own research? Might be able to apply to their own research. Okay. If you have remaining questions, what kinds of questions are those? Are these about neural representations? What are they about? Yeah. Yeah. Yeah, so it will constrain the implementation, but you often have to make additional assumptions. So, for example, in much of this earlier work that I barely got to talk about, the neural implementation here, you have to make some additional assumptions about the neural code, but then you can make predictions for the kind of neural operations that would implement a particular Bayesian computation. You can also do something with simple neural networks where you still have the solution informed by the Bayesian solution, or you can use the Bayesian solution to better interpret what the neural network is doing. So there is some evidence for interplay between the implementational level and the Bayesian level. And these days, even many neural networks have Bayesian flavors to them. And the reason for that is in part because of one-shot learning, the fact that I mentioned that very often kids learn from very few examples. It's also because neural networks are notoriously uninterpretable. So in order to deal with that, you sometimes want to structure them a little bit better to avoid adversarial examples, for example, adversarial attacks. And then these Bayesian methods, they could give better structure to the neural networks. And a third reason is to build in notions of uncertainty into neural networks. So all of those live in the intersection between implementation and Bayesian ideas. Okay, very good. So if you are still a little bit shaky about whether you can use these methods yourself, I just wanted to say, as a way of concluding, that all of this stuff took me maybe 17 years to learn. Doesn't mean that it will take you 17 years to learn, but that means that if you have been trying this for a year or so and you still have many open questions, that's normal. And if you haven't tried this before and you just want to get into it, I'm sure you can. There's no reason why you wouldn't be able to successfully model behavior. I'm personally super interested in modeling behavior, as you can tell, so if you have any questions, any interesting behavior that has maybe some flavor of uncertainty, always feel free to talk to me. And finally, I want to thank these amazing teaching assistants. Please give them a big round of applause. The organizers actually made a generous honorarium available, but I actually didn't read my email carefully, so I didn't tell my teaching assistants that, and they are actually they volunteer at the moment when I asked them to sign up as TAs. Also, thanks to Memming for organizing this and having me as a speaker, and Leslie for a lot of administrative support. Thank you all for coming, and good job, everyone. Thank you.